Okay, with that, let's jump into parallelism and heterogeneity. And let me hide this floating meeting controls. So what we're going to cover today and tomorrow are issues in parallelism and heterogeneous multi-core systems and bottleneck acceleration. It's probably unlikely that we're going to start multiprocessors tomorrow, although we will talk about multiprocessors, not except in a heterogeneous sense, let's say, in this case. And these are some readings that we're going to cover. And if you're interested, you can take a look at them. I'm going to mention them. But let me talk about heterogeneity. We've seen a lot of examples of heterogeneity, actually, but let me give you a quick, let's say, perspective on design heterogeneity. So heterogeneity, asymmetry also means heterogeneity, and it leads to specialization, basically. As I said, they have the same meaning, and you can contrast these with homogeneity and symmetry. And heterogeneity is a very general system design concept in general, and also a life concept. We will discuss this, but everything in life is heterogeneous. There's variation in everything, basically. So, and the basic idea, if you have to describe this basic idea of heterogeneity, it's this. Instead of having multiple instances of a resource to be the same, in other words, heterogeneous or symmetric, design some of the instances to be different. In other words, heterogeneous or asymmetric. That's the idea. And in some cases, this is heterogeneous design, of course, right? In some cases, it may not be even under your control, right? Resources may be different by nature, right? And this is really the variation, manufacturing variation that we discussed, right? So there are multiple reasons for heterogeneity. One is you get heterogeneity because of the way nature is. Nature is heterogeneous, and as a result, manufacturing processes are heterogeneous. So you get heterogeneous refresh rates, for example. You get heterogeneous frequencies. You get variation in device latencies and across devices and within devices. So that's heterogeneity by nature, let's say. There's also heterogeneity by design, which is this idea. You design some instances explicitly to be different, to be heterogeneous, so that you can take advantage of that difference. And let's take a look at what that difference could lead to. Basically, these different instances can be optimized to be more efficient in executing different types of workloads or satisfying different requirements and goals. And these are both valid reasons for designing heterogeneous systems, workloads and different metrics, let's say different goals. Essentially, heterogeneity enables specialization and customization to some degree to both workloads as well as goals. Okay, so these are the two major reasons, in my opinion, why you need asymmetry and heterogeneity in design. Different workloads executing in a system can have different behavior. And the same workload, the same application can have different behavior at different times as well. And systems need to be designed to satisfy different metrics at the same time. And in order to be able to cater for different workloads and different metrics, you want asymmetry. So different applications can have different behavior, obviously. Different execution phase of a single application can have different behavior. The same application executing at different times can have different behavior due to different input sets and dynamic events, user interactions. And there are many, many examples of this. Locality is heterogeneous. Predictability of branches is heterogeneous. Parallelism is heterogeneous. Data dependencies are heterogeneous. As we will see, serial fraction in a parallel program are heterogeneous. Bottlenecks are quite heterogeneous. And we have seen that interference characteristics across applications are quite heterogeneous as well. So this is very dynamic as well as heterogeneous in the end. So if you look at the second point, there's almost never a single goal in design. In fact, you can remove that almost. Depending on design points, you have multiple designs, multiple goals, and you have a priority across those goals, of course, right? Usually you have a priority saying performance is the highest goal for me. Energy is second highest, for example, or maybe they're equal somehow. Basically, but there's almost never a single goal. Functionality, reliability is a goal also, even though they may not be implicitly stated in many cases. And you can see there are many metrics, right? Performance, energy, fairness, predictability, reliability. I'm not going to read all of these, but you can have resource level metrics as well as system level metrics. So the problem is, if you do a symmetric design assumes that you have this one size fits all, right? It tries to fit a single size design to all workloads and metrics. This is like a single size shirt, right? You have a t-shirt that you want to buy. They basically advertised as like a fixed size and everybody can wear it. But you know that it's not going to be possible that everybody can wear it, right? Because everybody's different, right? So symmetric design is like that. It's very difficult to come up with a single design, basically. Some people who are going to wear that t-shirt will have a lot of space in the t-shirt. Some people who wear that t-shirt will not have any space in the t-shirt. They will not be able to wear it, right? So it's the same thing basically in this case. it's very difficult to come up with a design that satisfies all workloads, even for a single metric. We're talking about even a single metric right now. Even for performance, you cannot satisfy the demands of all workloads if you're symmetric. And if you add multiple metrics at the same time, it's very difficult to come up with a single design that's symmetric that satisfies all design metrics at the same time. And this holds true for different system components or resources. And we've discussed several system components so far: cores, caches, memory, controls, interconnect, disk, servers, as well as I would also consider power and energy resources, thermals as resources, algorithms and policies as well. And I think I like thinking things of pictorially. And if you look at a symmetric design, it looks like this. Whatever resources this may be, C may be cores, for example, in this case. If you look at these symmetric resources, energy and performance is suboptimal for different workload behaviors over here. It's one size fits all. If your workload demands a core that's more powerful than this little core over here, too bad, you don't get it. If your workload doesn't want the inefficiency of the small core, too bad, you'll be inefficient, right? That's the idea. Whereas if you're asymmetric, you enable choice, basically. It looks like this. You have different types of cores in this case, or different types of resources. And you enable customization and adaptation. Because processing requirements vary across workloads, applications, and phases, now you can decide to execute the code on the best fit resources, minimal energy, adequate performance, and the best fit resource is now flexible. If your computation demands a powerful core, you execute the computation on C1. If your computation doesn't demand a powerful core, you choose one of the C5s to execute the computation, right? If it's medium, you choose one of the C2s. Now, asymmetric can be nice if it's configurable also, right? If you can somehow configure the symmetric one to become asymmetric, that could be good also, right? Basically, symmetric, rigid symmetric is not good. Configurable symmetric may be essentially okay because at least asymmetric in the end, right? So configurability or reconfigurability helps asymmetry because fundamentally configurable or reconfigurable systems are asymmetric systems, or you can create asymmetry using configurability or reconfigurability. And clearly we have seen examples before. I'm going to remind you of some of these. In digital design and computer architecture, for example, you said Cray-1 design, the fastest supercomputer of its time, was not a completely vector computer. Vector computation was important. That's how you do matrix multiplication, for example, right? But it had the fastest scalar pipeline of its time. Why? Because scalar part was the bottlenecking computation. So it was a heterogeneous design. Modern processors have scalar instructions and SIMD instructions. Decoupled access execute that we discussed in digital design. You have a separate access and execute processors. These are examples of heterogeneity. We've seen thread cluster memory scheduling, different memory scheduling policies for different thread clusters. We've seen the idea of RAIDer, heterogeneous refresh rates in DRAM. We've seen heterogeneous latency DRAM, different examples of it. Tiered latency DRAM was one example, but exploiting process variation also was another example, right? Hybrid memory systems that we just discussed is a clear example of this. And there are many types of hybrid memory systems that we discussed also, including for different metrics, right? Performance, endurance, as well as reliability and cost, as we discussed, right? And there are also heterogeneous cache replacement policies that employ multiple different cache replacement policies together. For example, least recently used and random, or memory level parallelism array policies. And this is just to jog your memory if you took digital design and computer architecture. If you look at Cray-1, even heterogeneity is a very old idea, as you can see, and it's been employed in systems. You can see that there are vector units and there are scalar units. And even in vector units, there are floating point units and integer units, right? So these are different. And access parts are different from execute parts also, even in Cray-1. Okay, hybrid memory systems we talked about. Remember thread cluster memory scheduling, different policies we talked about. I'm not going to talk about that again since we talked about it multiple times. Heterogeneous refresh rates, another example. Heterogeneous latency memory, tiered latency DRAM, as we discussed, is another example, right? You get the best of multiple metrics as much as possible. I'm going through this relatively quickly since we've discussed all of these in earlier lectures, but you get small area and low latency at the same time in this case, right? But you need to manage it because it's heterogeneous. So heterogeneous systems always require management, basically, as you can see in the example of tiered latency DRAM, as we have seen it. As we have seen also in thread cluster memory scheduling, right? You need management in terms of deciding which threads should be treated how in terms of different policies. This is something you have not seen perhaps, but we have heterogeneous interconnects also. Later in the course, we will try to discuss interconnects in more detail. But this is an example multi-core system, a very embedded multi-core system in Tylera, you have 5 different networks. 4 of them are packet switched. 1 of them is circuit switched. So these are different types of operation also. And some of them handle cache requests. Some of them, one network handles cache requests. One network handles cache responses. One network handles IO requests. One network handles core-to-core messaging. And the circuit switch network handles streaming data from one place to another place, one node to another node. And these are designed to be heterogeneous so that they can cater to different types of requests without interference between different requests, right? That's the idea, basically. You can customize the design of a network to different requests that are flowing through the network as well. So basically, heterogeneity is everywhere in the systems we design today, maybe not to the extreme extent that we're going to see in the future, but it's everywhere. And in all resources, it makes sense because different workloads have different requirements from the resources, and resources need to cater for different metrics as well. And also, this is very natural, I think. As we have discussed in the past, heterogeneity is abundant in life, both in nature and human-made components. Humans are clearly heterogeneous, right? We have genetic diversity. It's called genetic variation. And we have a lot of variation. No two human is exactly the same. Even if their genetic diversity is the same, then their interactions with the nature is not the same. As a result, for example, people who are completely the same in terms of their genetic material turn out to be very different in terms of human beings when you interact with them. For example, twins are like that, right? Cells are heterogeneous. They're specialized for different tasks. Organs are heterogeneous. So I'm giving a lot of examples from biology over here, but these are clearly, our brain is very heterogeneous, right? As we discussed in the past, it's specialized for different tasks. Cars are very heterogeneous today, right? We design extremely different cars. We don't have a one-size-fits-all car for everyone. So it doesn't make sense to design processors to be one-size-fits-all also. Buildings are heterogeneous. Wherever you're sitting right now is very different. Rooms are heterogeneous, etc. So I can keep going, but it becomes a little boring after this. But it's good to realize it, I think, that everything in life is heterogeneous also. And there's a reason for that heterogeneity. Okay, so one thing I will mention, I think, is general purpose versus special purpose. We've been talking about general purpose, special purpose. I also talked about in the last lecture or last part of this lecture as well, right? General purpose clearly tries to do computation, tries to accomplish any computation, right? But it's not good. It's not extremely good at every computation, right? Special purpose is something that's designed specifically for a particular type of computation workload. For example, only thing you can do is execute neural networks, right? The only thing you can do is factor numbers, for example, factor numbers at polynomial time, right? That sounds good, right? But these two things are very different, right? General purpose can do everything. Special purpose can do one task extremely efficiently. General purpose may not be good at doing every task extremely efficiently, clearly, right? Or it may not be able to do some tasks, where it may be able to do some tasks extremely inefficiently, right? It's so inefficiently that we don't want to do it with general purpose machines, right? So asymmetry is a way of enabling specialization, enabling the special purpose system in a general purpose substrate, let's say. So it bridges the gap between purely general purpose and purely special purpose. As I said, purely general purpose has a single design for every workload, every metric. You can throw any workload, past or present or future, and it's going to work okay on this general purpose system. Okay meaning okay in any metric, right? Whereas purely special purpose is designed for single design per workload or metric, and usually a combination of workload and metric in general. For example, very efficient neural network computation, right? Asymmetric is multiple sub-designs optimized for sets of workloads and metrics and that are and glued together. So it bridges the gap in a nice manner, in my opinion. As a result, it gets the best of both general purpose and special purpose worlds. So today's system designs, I'll show you a picture of Apple M1 again, for example. You have different types of accelerators over there. Those accelerators are special purpose. So some of them are purely special purpose, but they're glued into a general purpose substrate, right? Basically, that's what asymmetry and heterogeneity is. Okay, so the goal of a good asymmetric design is to get the best of both general purpose and special purpose, in my opinion, as much as possible. And ideally, you will get the best of any special purpose mechanism as well. Okay, so let's talk about asymmetry advantages and disadvantages. These are general advantages of asymmetric designs over symmetric design. Clearly, you can enable optimization of multiple metrics with asymmetry. You can enable better adaptation of to workload behavior. you can provide special purpose benefits with general purpose usability and flexibility, hopefully. But there are downsides also. Clearly, there's higher overhead and more complexity in design and verification because you have more components. In symmetric design, you have a single component, you stamp it out. In heterogeneous design, unfortunately, you don't have that luxury. You have to design each component, each heterogeneous component, and then glue them together. And you have, as a result, because these things are different from each other, you have higher overhead in management. Scheduling onto asymmetric components is not easy, as we have discussed with hybrid memories, for example, right? We've seen this very well in hybrid memories. If asymmetry is very high between the two different components, managing even multiple metrics across the different components is not easy. And there's clearly overhead in switching between multiple components that leads to degradation. And we have seen this in hybrid memories also. Whenever you move data from one memory type to another memory type, you incur overhead in terms of bandwidth consumption and also cache capacity, right? So let me give you another example. And we've seen this also. Modern processors integrate general purpose cores and GPUs, right? So we have CPU, GPU systems. And this leads to heterogeneity in execution models and ISAs as well. So it's not just heterogeneity in microarchitecture, like we've been discussing so far, but it's also heterogeneity in execution models. The CPU and GPU are programmed in multiple different ways. Add hardware accelerators on top of it, the machine learning accelerators. They have potentially other execution models than ISAs. Now we have actually a collection of different execution models and ISAs in a general purpose substrate, and you need to make them work together. And it's good to contrast it with heterogeneity in only microarchitecture, where you have a single execution model and single ISA, and then you handle the heterogeneity in the microarchitecture without exposing to programmer. But today's systems and going forward, we will have both heterogeneity in microarchitecture, as well as we already have heterogeneity in execution models and ISAs. So we have both today, actually, in today's systems. So the question becomes how to actually take advantage of it. And I think heterogeneity can enable solving of many key problems in future systems. So this is one example I've covered based on what we have covered so far. Clearly, memory system is a big problem. Energy is a big problem because it limits our scalability. And energy, well, efficiency is a big problem, but efficiency is a combination of both performance and energy, and it limits our scalability. And predictability and robustness are big problems also. And clearly, we've discussed these problems, so I'm not going to go through the importance of these. But one thing I will mention is efficiency enables more scalable systems. It can enable new applications. And more efficient systems enable better user experience, so it can enable new usage models as well. So these can enable new platforms too. And we've discussed predictability and robustness, so I'm not going to talk about that. So these are clearly three key future problems, and asymmetric designs can help solve these problems. We've seen examples of this in our past lectures. So in today's and tomorrow's lectures, we're especially going to focus on performance and energy, especially in computation. Can we basically design much more efficient systems that can be much more scalable going into the future by executing some difficult computations much more efficiently? And hopefully these will enable more scalable systems and better user experience as well. Okay, I'm going to talk about these, but before that, I will give you some more examples. This may be an old slide actually, but clearly we have integrated CPU and GPU systems. Some of the earliest ones are Intel Sandy Bridge, CPU with many hardware accelerators and SoC, like your cell phone. Heterogeneous multi-core systems already exist. CPU plus FPGA systems already exist. So there are many examples. So commercially, this is already happening as well. And commercially, this is going to increasingly happen. Basically, we'll have increasing heterogeneity in the agents, which is computation components, heterogeneous memories, some of which will do computation as well, and heterogeneous interconnects. So I think all of our components are going to be heterogeneous, if not already heterogeneous. If they're already heterogeneous, the level of heterogeneity is going to increase in these components. So clearly, this is not easy to program, because programming, managing these resources for both computation, communication, and storage and memory is not easy. And we need to find good ways of managing these resources. But this is a huge opportunity for scalability and parallelism, because we have a lot of parallelism potential across all of these resources, whether they are CPU, whether they are computation resources or interconnect resources or memory resources. And again, memory resources can be computation resources as well. Keep that in mind. Some of these memory resources are also accelerators, right? Hardware accelerators, as we discussed in the last lecture. And again, just to put an example into the picture, I like picking on Apple's M1 processor because it's a very nice example. As you can see, we already have high performance and efficient cores, two different types of cores, GPUs, neural engines, and some of the things that are not discussed also in this, some other accelerators. So clearly, heterogeneity is everywhere in our systems today. Let me give you a historical perspective as well, because multi-core systems, when they started, were not heterogeneous. So I think it's good to think about this, let's say, dichotomy between large cores and small cores, and think about where people have landed. Because this is actually this, let me show you. This idea of putting CPUs and GPUs together and putting multiple different types of cores in the same substrate is not a new idea. It's been done in recent processors, and that's good because that's a step in the right direction. But this is an idea that dates back as early as 2002 or so. When multi-core systems were designed, actually, they were designed as symmetric cores. Basically, there was a good reason for them. People were having difficulty scaling a single core. So they wanted to put simpler and lower power cores than a single core and have many of them on a single chip so that they can enable large scale parallelism. But they started putting different types of cores. So you can see that these are different multi-core systems. Some of these are extremely small cores over here. These are examples over here. Well, GPUs also have cores. Whatever they call are debatable. They call cores is debatable, of course, but they have some sort of cores also, right? And these are also small cores. So ideally, what you want, you've seen the slide before. You want n times the performance with n times the cores when you parallelize an application on n cores, right? So we're talking about parallelizing an application, a single application right now, not multiple applications. What we get today is Amdahl's law. Basically, we have a serial bottleneck. We're going to talk a lot about Amdahl's law going forward. How many people know about Amdahl's law? Just to see a show of hands. So some people. How many people do not know about Amdahl's law? Okay, that's good. That's good. Then you have not taken digital design and computer architecture probably, or maybe you don't remember it from there, but that's fine. But Amdahl's law, it says that there's a serial bottleneck in programs that limits how much you can parallelize a program. And clearly it's a function of your algorithm as well as your program design. And we're going to talk about that. But we also get bottlenecks in the parallel portion also. Even if you parallelize your program, the parallel portion is not perfectly parallel. So assume that Amdahl's law doesn't exist. You got rid of all of your serial bottleneck. There's still bottlenecks in your parallel portion. And we've discussed some of them, actually. I'm going to discuss more of them. So, okay, let's talk about Amdahl's law. We're going to see this more in multiprocessors again as well. But basically, Amdahl's law states very simply that you have a parallelizable fraction of a program, and you have a non-parallelizable part. Parallelizable fraction is explained as f, and non-parallelizable part is 1 minus f. Okay, and it's introduced in this seminal paper by Gene Amdahl, who was actually the chief architect of IBM's 360 line of processors. And basically, in this paper, he argued that there are some workloads that we cannot parallelize. As a result, the capability of multiprocessors is very limited. So single processor, we should still keep improving single processor performance. So what does Amdahl's law state? Amdahl's law state that, let's assume that you have n number of processors. Parallelizable fraction of the program reduces to f over n in terms of, let's say, execution time. And non-parallelizable fraction, you cannot do much about it, basically. So parallelizable fraction goes down to f over n because it's perfectly parallelizable. Non-parallelizable portion stays at 1 minus f. As a result, speed up with n processor becomes this equation. Does that make sense? So a parallelizable fraction speeds up by n. Non-parallelizable fraction doesn't speed up at all. As a result, speed up equation looks like this. And that's the speed up with n processors. And maximum speed up is limited by that number f right now. So if f is, let's say, 50%, parallelizable portion is 50%, this number over here becomes 0.5, right? This number over here becomes 0 as n goes to infinity, because we're thinking perfect parallelization, right? As n goes to infinity, the parallelizable fraction of the program becomes non-existent in terms of execution time. So you're bottlenecked by the non-parallelizable portion, meaning that if n, even if you have infinite number of processors, if f is 0.5, you get only a speed up of 2. That doesn't sound very good, right? An infinite number of processors and I get a speed up of 2. That's not good. I should really improve my parallelizable fraction. Right? Even if you have a parallelizable fraction of 90%, 0.9, your speed up, your maximum speed up achievable is 10, even if you throw an infinite number of processors to the problem. So basically, that's how important the serial bottleneck is. Even if the serial bottleneck is 0.01%, your maximum speed up is 100x, right? 100. 100 is nothing compared to infinite number of processors, right? You're very much bottlenecked, basically. Unless you make the parallelizable portion 100%, you still have Amdahl's law. Okay, but parallel portion is also usually not perfectly parallel, as we have discussed, right? You have synchronization overhead, meaning you have updates to shared data. So you have locking mechanisms. As a result, not all threads can be executing in parallel at any given time. Even though you're in a parallel portion, some thread may be updating some shared data, right? We discussed this earlier when we talked about parallel application memory scheduling. We're going to discuss this even more. Load imbalanced overhead. Parallelization may not be perfect. So some threads may have more work, some threads may have less work. Remember the example I gave from threads counting the characters in a book, and you partition the book such that each thread gets 100 pages. The thread that got 100 pages of figures has nothing to do because there are no characters in those, right? As a result, it finishes its work much earlier. As a result, your program is not perfectly parallel. Your parallelizable fraction of the program is not perfectly parallel. So this is very important also. So resource sharing overhead, we've seen contention among processors, right? You have many processors contending for some resource, and one of them has to wait when the other is accessing that resource. We've seen this in memory scheduling, for example. This is present in caches. This is present in hybrid memories, etc. As a result, even though you may think that you parallelize your program and you're executing on multiple different processors nicely, because of interference across different resource, across the same shared resource between different threads, you get delays. And that leads to this F over N being incorrect. Basically, this is not a simple equation like F over N. You need to take into account the bottlenecks in the parallel portion as well. Okay, so hopefully that's interesting. We're going to talk about basically how to speed up the serial bottleneck as well as this parallel bottlenecks in today's remaining part as well as tomorrow's lecture. So basically, the problem is many parallel programs cannot be parallelized completely. As we discussed, there are sequential, there are serialized code sections. Sequential code portions are an extreme example. This is Amdahl's serial bottleneck, but there are critical sections, there are barriers, and there are limiter stages in pipeline programs that we have discussed in an earlier lecture as well. We're going to discuss more. And these serialized code sections reduce performance, limit scalability, as well as waste energy. Because you basically, let's say you dedicate one thread, and the thread has nothing to do in the core, and the core is basically waiting for other cores to finish, right? It limits scalability because you're not utilizing your cores well. It's wasting energy. It's reducing your performance. It's doing everything that I discussed over here. Let me give you one example. MySQL is a commonly used database, open source database. It's actually being improved by many database companies also. Basically, in MySQL, a thread opens the database tables, and then it performs operations on the tables, rows and columns it opens basically. Performing operations in parallel because you get the lock on the database table, so you can parallelize the operations. But opening the database tables requires access to open tables cache, which is a shared data structure. And it turns out you need a critical section to access this. And this is what your performance looks like if you have a symmetric cores. Basically, you have some number of cores going from 1 to 32 in this particular case, symmetric cores. And this is what your speed up looks like. Basically, going from 1 to, let's say, 15 or 16 cores over here, you get good speed up. 6x. It's not perfect, right? Ideally, I would expect going from 1 to 16 cores, I would expect 16x speed up, but I'm getting 6, which is still better than getting less. So clearly, there are some bottlenecks in the parallel portion, which is critical sections, for example. That's one example. Interference, resource sharing, cache coherence overheads are other examples. But there's something interesting happening. As you keep adding more cores and more threads, your performance starts reducing now, meaning your speed up starts reducing. This is speed up compared to a single core execution, single thread execution. It maximizes over here. It starts reducing over here. Now your overheads are too high. Why? Some of these are contention overheads because cache coherence overheads, because the data that you need to access, the locking that you need to do for the critical section, the lock is traveling between the caches. Some of it is memory bandwidth bottlenecks, potentially. Some of it is other interference issues that you have. They're basically reducing your performance because you basically overloaded your system with too many threads. and the overheads are too much, basically. The parallelism, additional parallelism, is not overcoming the overheads that are in the system. Okay, so this is symmetric. But today, with a symmetric system, you can actually make it much better. And we will see an example of a symmetric system where we have a asymmetric multi-core, and we execute these critical sections on a large core that is able to execute these critical sections fast. So hopefully that'll be interesting. But we will probably get to it tomorrow. So asymmetric designs can enable better scalability. I think this is called a scalability curve. Basically, this shows that how much your performance scales with the number of threads or chip area, number of cores, basically. Ideally, you want linear scaling, right? As we will see in our multiprocessors lecture, linear scaling is the best. If you have super linear scaling, then probably you're doing something wrong, meaning you either have an unfair comparison or you're adding more resources than just cores. But you usually get curves that look like this. For both of these actually are reasonable curves that you can see today. Usually the scaling is sublinear with number of cores. But ideally, you would like to get as linear as possible. Okay, so basically, we have different demands in different code sections. It's good to recognize that. What we want is, in a serialized code section, we want one powerful large core. In a parallel code section, we probably want many wimpy small cores, because parallel code section is extremely parallel. Serialized code section is only one thread is executing, usually, right? In Amdahl serial bottleneck, for example. So clearly, these two conflict with each other. If you have a single powerful core, you cannot have many cores. And a small core is much more energy efficient and area efficient than a large core. So you can put many small cores in the same area. Let's take a look at these large versus small cores. Large core has a lot of techniques to exploit parallelism, instruction level parallelism, out of order, white fetch, deeper pipelines, aggressive branch prediction, multiple function lists, trace caches, etc. Small core is very small, basically very wimpy, in order, narrow fetch, shallow pipeline, simple branch predictor, few functional units. And large cores are usually power inefficient. For example, this is a good rule of thumb. You get 2x the performance for 4x the area or power. And this is from this paper from Intel, actually. It's a nice paper. It was published in ICCD in 2004, where they basically show the difference between large and small cores. Basically, large core can be very good at performance. You can see 5 to 8x, but its power consumption is much higher. Its normalized energy per instruction is also much higher. So small cores are actually much more energy efficient, but they're not the highest performance, absolutely, as you can see, right? And I recommend you reading that paper if you're interested. So multi-core evolution happened that way, basically. People decided symmetric cores were good to start with. And IBM Power 4, for example, was one of the first multi-core systems. You can see the paper from 2002. It's actually a beautiful paper that I would recommend you to read. IBM used to write papers about its microarchitectures and system. And this is very nice. And you can see that it's essentially two cores, two powerful cores. You can see they're very powerful cores by that time standards. And these are symmetric though. So they could not get the best of both worlds. IBM Power 5 added multi-threading into each of the cores without changing the core structure that much. They're still symmetric cores. On the other hand, people took the exact opposite extreme. Sun Niagara, for example, when Sun was around, they decided to design this multi-core system that are heavily multi-core. They have 8 cores, as you can see, not 2 cores, and each core has 4 threads, so they have 32 threads over here. And each core is very wimpy, very simple core. They basically said, we don't need large cores. We're executing these workloads that don't need large cores, commercial workloads. Well, they should have known better, basically. But basically, this is how simple the cores are. You can see it's very simple. It's fine-grained, multi-threaded, 6-stage, dual issue in order. They even had a shared floating point unit that they fixed in larger incarnations of Niagara. So basically, this doesn't perform well in code sections that demand high performance. So let's take a look at, let's analyze these 2 different cores. What we want is in a serialized code section, one powerful large core, meaning like something like IBM Power 4. In a parallel code section, we want many wimpy small cores, something like Sun Niagara. But we cannot get the best of both worlds because these 2 conflict with each other, as we discussed, right? The question is, can we get the best of both worlds? Let's take a look at, let's do some quick analyses, basically. Assume that small core takes an area budget of 1 and has performance of 1, and a large core takes an area budget of 4 and has performance of 2. This is what we'll assume. A large approach looks like IBM Power 4, Power 5, and AMD and Intel took initially, but later they became heterogeneous, of course. So you get high performance on single thread serial code sections. So you get 2 units of performance based on the equation that I showed you. But you get low throughput on parallel program portions. You get 8 units, as you can see, because each of them gives you 2 units, and you have 4 of them. 4 times 2 is 8. Tile small, it gets high throughput. This is similar to some like Tilera Tile and Sun Niagara. Intel Larrabee was another example. None of these were extremely successful, let's say, because they actually reduced performance compared to large cores. But you get very high throughput on the parallel part, 16 units, but you get low performance on the serial part. Your performance even reduces compared to a large core, basically, 1 unit. So basically, Tile large is good for high performance on single threads, but low throughput. Tile small is high throughput, but it has low performance on single thread serial part. In fact, if you go from Tile large to Tile small, large core to small core, you lose market potentially, as has happened to some of these companies, because you reduce your single thread performance. And people do need single thread performance in cases where that single thread performance is critical. And there are many cases where that is true, as we will also see tomorrow. And the idea in asymmetric multicore is have both large and small on the same chip. And this is performance asymmetry, basically. And that's what brings us to asymmetric multicore. And this is what it looks like, basically. You have a large core. And this is just one example, right? You can have 1 large core, 12 small cores in this particular case. You can accelerate the serial parts, the difficult to code sections, and get the performance of 2 units. And you can execute the parallel part on small cores as well as the large core, so that you can get high throughput. You get 12 throughput over here, plus 2 in the large core. You get 14 units. But if you make large core multi-threaded, you can easily get to 16 as well. So hopefully these calculations are interesting. So now you can actually have accelerate serial bottlenecks. You can have whenever you have single thread, you execute on the large core. Whenever you have multiple threads, you distribute them to smaller cores. So the parallel portion of the program can execute on the small cores, whereas serial portion of the program can execute on the large cores. And this is where accelerating the serial bottlenecks can come into play. Now, if you actually do the performance versus parallelism assumptions, again, this is what the equation looks like. I've already given you, actually. But when you Tile large, this is very good for serial performance. You get 2, not good for parallel throughput. When you Tile small, great for parallel throughput, but not good for serial performance. Asymmetric multicore tries to achieve the best of both worlds. Good for serial performance, good for parallel throughput, and it can be better if you actually make the large core multi-threaded. Now you could argue that Tile large can also make the large core multi-threaded. Yes, absolutely. So if you make the large cores more customizable, configurable, sure, you can actually get higher throughput, parallel throughput as well. So basically, if you modify Amdahl's law for an asymmetric multiprocessor, it starts looking like this. It's a bit more complicated, but now this is simplified Amdahl's law for an asymmetric multi-core processor. Serial portions execute on the large core, parallel portions execute on both small and large cores. F is still the parallelizable fraction of the program. L is the number of large processors. S is the number of small processors. X is the speed up of a large processor over a small one. Now, your serial fraction also gets accelerated by X, right? Because the base processor is a small processor. Your serial fraction executes by 1 minus F gets divided by X because you're executing on a large core, not all small cores. Your parallel fraction gets executed on small cores plus 1 large core. And 1 large core's benefit is X times L because it's higher performance than a small core. So you can do these equations, plug these numbers yourself if you're interested. And if you basically, if you do this, you can get rid of some of the serial bottlenecks because your serial bottleneck now, executes on the large core, but you can potentially execute these parallel portions, bottlenecks in the parallel portion, also in the large core, and take advantage of this equation by executing those bottlenecked parts in the parallel portion over here. And in the next lecture, we're going to see examples of how we can actually execute bottlenecks in the parallel portion in the large core so that we can speed up multi-threaded programs significantly. Okay. Any questions? Yes, there's one question. Please go ahead.
Does the study take into account multi-programming workloads? If you had multiple applications, wouldn't it be worse if you decrease the number of large cores? Mm-hmm. And if you have multiple applications that then contend, and one application gets, well, mm-hmm. Some applications get the large cores and many applications get the small cores, wouldn't that make performance worse?
Yeah, so that's an excellent question, basically. I mean, here I just give an example of 1 large core, but I think to scale up the system, you really need multiple large cores and multiple many small cores, just like what's happening in industry today. So you're absolutely right. Having one large core is not enough really for a scalable system when you want multi-program workloads. But in this lecture and the next lecture, most of next lecture, not all of next lecture, we're going to talk about a single workload and how to manage heterogeneity for a single multi-threaded workload. But your point is absolutely crucial. If you have multiple workloads, we're going to talk about how to manage multiple workloads also. But if you have multiple workloads, having multiple different large cores is actually extremely important. Okay. Yes, there's another question. If there's no one contending for the room, we can continue, I think, with questions. You're the ones who are seeing it, but go ahead.
Is the main cost, I mean, is the reason for the inefficiency that clocking your core faster is just not that scalable? So it costs a lot more energy to make it twice as fast?
Yeah, so that's a good question also. Basically, I think what you're saying is, why not clock these small cores to be faster, right? You can do that, yes, but it's energy inefficient. And also, you don't get all the benefits of the large core, basically. Because large core provides benefit more than just frequency, right? It's all of these microarchitectural instruction per cycle improving techniques. Like you have large caches, for example. You have out-of-order execution, heavy levels of out-of-order execution. So you get benefits from that as well. But yes, if you do the equation in terms of energy, these should be perhaps energy neutral as well. And clocking all of these small cores to be extremely high frequency is not going to work very well because it's going to go against your power budget.
Oh yeah, I think I was just trying to answer my mind, like I got sort of inconsistent or like a difference between memory and computation, because in memory it seems like the reason why we wanted to increase capacity rather than just stack 100 separate sticks of RAM together is because you get better energy efficiency when you try to fit more into one chip. But for computation, it seems like it's the opposite. When you try to fit more into one chip, you actually lose your efficiency. So I guess, yeah.
Well, I think I'm not entirely convinced about the efficiency argument that you make. I think still, for example, you can have a lot of small cores, and you can run them relatively slow, but because of the parallelism, you can get a lot of efficiency, right? So lowering the frequency can actually make you much more energy efficient by packing many small cores over here, as long as you can parallelize your program extremely well. Does that make sense?
I think so.
Okay.
And I guess just a question about the the earlier part of the lecture on symmetry. Sure. Would you say, which mindset would you agree with more? To design things trying to respect symmetry until it makes no sense to do so, and it should be heterogeneous, or to have heterogeneous as the default mindset, and then continue with that until it doesn't make any more sense to deal with the overheads.
Yeah, so that's I mean, that's also a good question, right? I mean, I think it needs to be examined in any design that you are looking at, right? So if you're looking at a computer system design, I mean, certainly symmetry has benefits, but again, if you're not achieving your goals on efficiency and performance, I think heterogeneity can be the default also, right? I think in today's systems, probably the mindset should be heterogeneity from default, because we have kind of exhausted the limits of symmetry, and with heterogeneity we can make things much more efficient by building accelerators in our systems. But again, if you take this to the extreme, it may not be wieldy as well, right? You don't want to build an accelerator for every single program out in the world, right? So it becomes a balancing act at some point, right? How do you classify subsets of workloads that are important enough so that you can design asymmetry into your system to cater to those workloads? But I would argue today's systems, the mindset has to be heterogeneous. Maybe that was not the case 20 years ago.
That makes sense. Thank you.
Sure. Okay, very good questions. It doesn't look like anyone is taking over the room, but we should stop regardless. So I think tomorrow we're going to start from here. Basically, maybe I'll briefly mention the slide also. But basically, I've already said this. What I said was we would like to identify critical parts of a program, dynamically identify them, dynamically identify those critical parts of a program that cause serialization and execute them on a large core. And this is a mindset. Executing them on a large core is just one example of accelerating them. You can come up with other ways of accelerating them, right? We have seen, for example, parallel application memory scheduling. But we will see how to identify these different code portions and also how to accelerate them and what goes into the challenges of this sort of bottleneck acceleration. But you can also free your mind and think critically and say, oh, there may be other ways of accelerating these important pieces of code, and depending on their bottlenecks, of course.
Okay. Yeah, welcome everyone to our lecture 18. We're going to continue parallelism and heterogeneity today, and hopefully we'll finish it. We're going to talk about bottleneck identification and acceleration, which is a really important topic in general, because that's how performance and scalability and efficiency improves, by identifying the key bottlenecks and accelerating them and moving on to the next bottleneck, if you will. And I'm going to give you an example of doing this in multi-threaded applications. How can we achieve much higher scalability and efficiency and performance and parallelism, essentially, in multi-threaded applications that aim to solve a single problem by utilizing many threads at the same time. And then we're going to hopefully have time to talk about multiprocessors in a more fundamental manner. Let's see if we can get to it by the end of the lecture. Okay, this lecture is also titled Bottleneck Acceleration, as you know. Yesterday, we started covering heterogeneous multi-core systems. If you remember, we talked about parallelism and heterogeneity. And today, we're going to look at using heterogeneous multi-core systems for bottleneck acceleration. So that's just one example of heterogeneity, clearly. Once you can identify bottlenecks, remember, I ended the last lecture yesterday. Once you can identify the bottlenecks, you can accelerate things in different ways, potentially accelerate an important bottleneck by customizing a core for it, potentially using an FPGA that's customized for that particular bottleneck, potentially using some other accelerator that's customized for that bottleneck, right? So keep that in mind while we discuss the ideas in this lecture today. The ideas in this lecture are mainly focused on heterogeneous multi-core, large core versus small cores that we started discussing yesterday, but there's no reason why you cannot potentially use other sorts of execution paradigms, GPUs, hardware accelerators, FPGAs, cores that are customized for the particular type of bottlenecks that we will see to accelerate bottlenecks. And that could make the ideas much more powerful, clearly. And these are some readings that we're going to cover. And we covered actually one of them yesterday, if you remember briefly. We may get to it again. Okay, this is what we were talking about yesterday, just to jog your memory, because this is such a fundamental equation. Amdahl's law is all about bottlenecks in the end as well, right? If you think about Amdahl's law, it expresses a program as a parallelizable fraction and a non-parallelizable fraction, f versus 1 minus f. It basically posits that you can perfectly parallelize the parallelizable fraction, and the non-parallelizable fraction becomes your bottleneck, assuming you have infinite number of processors n, right? And clearly, Amdahl also argued that non-parallelizable fraction of your program is bottleneck, and because that's high, multiprocessors may not provide very high performance benefits like we discussed yesterday. But there are also other bottlenecks. That's called the serial bottleneck. Amdahl's bottleneck is called the serial bottleneck. But there are also other bottlenecks in the parallel portion. And because parallel portion is not perfectly parallel as well, as we discussed yesterday. So just to remind you, these three major bottlenecks in the parallel portion are synchronization, load imbalance, and resource sharing. And these are very fundamental. This is also a great question to ask in interviews, for example, or exams, etc. I know of some companies who ask these questions in interviews, for example. And if you come up with another really fundamental bottleneck in the parallel portion, let me know. But these three cover essentially everything that I know, plus the serial bottleneck, of course, that's in the serial portion. Okay, this is the last slide that we covered yesterday. Essentially, bottlenecks serialize or lead to imbalance execution in the parallel portion. And these can benefit from a large core as well. Remember, we talked about executing the serial bottleneck, Amdahl serial bottleneck. If you have only one thread in your program, execute then the large core so that that thread gets accelerated, hopefully. Now, note that a large core doesn't guarantee that the thread executes fast, but it's more likely that the thread will execute fast on a large core, because large core has mechanisms to extract single thread performance much better than small cores. And usually they work better, but there may be cases where they don't work as good As a result, your performance with the large core may not be as high as you expect, may not be higher than the small core. This means that perhaps if you really want to accelerate a serial bottleneck, you really need to tailor the program, tailor the core to the bottleneck that you are looking at. So example bottlenecks we've already discussed over here. But the idea that we're going to pursue is to dynamically identify the core portions that cause serialization and execute them on a large core. And we're going to look at them one by one, if you will. So we're going to start with critical sections. Critical sections are important, as we discussed yesterday. And this is the first work that we did in this area when we thought that this problem was really important. And it's still really important, in my opinion. Going forward, these are some of the hard problems that we need to solve in computing. Okay, so we're going to talk about accelerated critical sections. So let's talk about critical sections and their impact on performance first. Let's do a thought experiment. It's always good to do a thought experiment whenever you're doing research, because that thought experiment enables you to understand the problem in a fundamental way. So what I'm going to show you is the execution time of essentially a loop that has 12 iterations, and it has 33% instructions inside a critical section, which are going to be marked with this red part. And the parallel part is going to be gray. So, okay, if you execute this loop with a single thread, clearly there's no overhead for critical sections, but you still have some part of the program in the critical section. And its execution looks like this. A bit boring, but it takes 12 time units, as you can see over here. If you execute this program with 2 threads, you can see that only 1 thread can be in the critical section at any given time. So the execution serializes when 1 thread is in the critical section and the other thread needs to enter the critical section. And the execution timeline looks like this. And you get almost linear speed up, except you don't get linear speed up because there's some waiting, idleness introduced to second thread over here because that first thread is in the critical section. Okay, so far so good, right? Critical section is not that bad for performance here. Okay, let's now see what happens if you actually parallelize this program with 3 threads. Now, if you have 3 threads, you can see that there's some more waiting that's caused over here. As a result, the execution of the 3 threads gets staggered, and the performance improvement is not 4. Basically, performance does not go down to 4 time units. It goes down to 4.5 or so time units. So again, it's not that bad, but you get some performance improvement going from 2 threads to 3 threads, but still there's some serialization. Okay, let's go from 3 threads to 4 threads. Now, what happens here is your performance doesn't improve anymore. Even though you're adding more threads and more cores into the system, your performance is the same as 3 threads in this idealized case, if you will. Why? Because the critical section execution is your bottleneck at this point. You can see that at any given point in time, there's some thread that's in a critical section. You can find basically put an arrow, put a line on the x-axis. At any given point in time, that line will cross a red portion over here, meaning that at any given point in time, there's a thread that's in the critical section, which means that at any given point in time, there's some other thread that's waiting. And that you can also prove by looking at this graph over here. So what happened was we parallelized the program too much, and the program became limited by the critical sections at this point. So you cannot parallelize it better because fundamentally you're limited by the critical section length over here. Now, if you add 1 more thread over here, your performance doesn't improve. In fact, it would degrade because critical sections are dictated by locks, right? And locks need to be communicated. And that communication causes additional overhead in terms of data movement of the lock or the movement of the lock between the caches of different processors, different cores. As a result, as you go to P5, P equals 5, P equals 6, P equals 7, your performance keeps degrading and it doesn't improve because you don't benefit from parallelism. All you're adding is overhead for managing the critical sections as you increase the thread count at that point. And this is very fundamental, as you can see. So basically, critical sections limit your throughput over here as well as scalability. Scalability means how many threads, at how many threads your performance saturates, meaning that's the highest performance you can get with the number of threads that you have. If you keep adding more threads, your performance actually goes down. Okay, now let's take a look at a case where critical sections accelerate by 2x magically in some way. Okay, with 1 thread, clearly you get better performance, not bad. With 2 threads, you get a little bit better performance, your waiting reduces, not bad. With 3 threads, you get better performance, that's not bad. Now with 4 threads, you get better performance compared to 3 threads, right? Because your critical sections are not the bottleneck anymore. if you look over here in this graph, in this set of lines, at any given point in time, it's not the case that there's a thread in the critical section. There are some threads that are executed. Some threads are, all threads are in the parallel section at some points in time, basically, meaning that critical section is not forming your bottleneck, in a critical path, let's say, in the entire execution. So now what happened is our performance improved by reducing the critical section time, as well as our scalability improved. Now performance saturates at a higher number of threads than 3. Probably it's 5 or something like that over here. You can do the calculation actually. If given these numbers, you can do the calculation. I believe it's 6 in this case. Okay, so basically our performance and scalability improved by accelerating critical sections because critical sections did not form the critical path of execution. So if you trace the critical path of execution over here, it always goes through the critical sections in this particular case when p equals 3 and we have the red graph over here. But that's not the case over here. It becomes the case when p equals 6 over here. Okay, so basically the takeaway is accelerating critical sections increases performance and scalability. And at which point your scalability improves depends on how bad your critical section percentage is as a fraction of your overall execution time. Clearly, if your fraction is 33%, your performance saturates at 3 threads in this particular case. If your fraction is only 5%, perhaps you can go up to 20 threads, right? Unless there are other bottlenecks, of course, right? We're just talking about critical sections in this particular case. So I think this is a very powerful thought experiment to see. Now, of course, then the question becomes how do you accelerate the critical sections? But let me actually give you some more data. Clearly, contention for critical sections leads to serial execution of threads in the parallel program portion. And contention for critical sections increase with the number of threads and limits scalability. And let's take a look at the example that I showed you in the previous lecture. We're going to look at MySQL, a database application with real inputs, with real applications, essentially, not the toy application that I showed you as a thought experiment earlier. Toy applications are always good because whenever you come up with a toy application, you can always be sure that there's some program in the real world that exhibits some characteristics that's similar to that toy application. Because there's so many programs that are out in the world, there's so many algorithms, whatever you come up with is usually going to be represented by some program. That's been my experience. That's been the experience that we have seen. So even though we call these toy applications, there are some applications that exhibit some similar behavior. Let's take a look at MySQL. I showed you this graph yesterday. This is the speed up that you get. This is the scalability curve or speed up curve that you get compared to one thread as you increase the chip area, as you increase the number of threads, essentially. You can see that the speed up saturates at about 17 threads, where you get 6x speed up compared to one thread, which is not bad in this case. So clearly, critical sections and other bottlenecks limit your scalability, so you don't get 16, the speed up of 16 with 16 threads, right? Okay, with asymmetric cores, we will show that we can actually get a much better speed up curve. So we can actually improve both scalability and performance. And we will see how we do that in this lecture. But basically, we're going to make a case for asymmetry. And asymmetry is, in the general sense, basically, do something different for these bottleneck portions such that you can accelerate them. That's the idea of asymmetry, right? Symmetry is everything is the same. Asymmetry is do something different for different code portions. So execution time of these sequential kernels, critical sections, and limiter stages must be short. And one could argue that it's the programmer's problem, right? It's difficult. Basically, somebody can give you a multi-core system and a lot of potential threads. And basically, you say that, oh, I cannot accelerate my program. And somebody can come back to and tell you that, oh, it's your problem as a programmer, fix it, right? And unfortunately, it's not as easy to fix these problems as a programmer because these are actually some of the tough problems in parallel programming, as we will see in the next lecture or next part of this lecture, because programmer may not necessarily know how to fix this problem because they may not have enough knowledge on how to actually parallelize their programs. Unfortunately, that's the case. They may not have enough domain-specific knowledge on how to parallelize a particular algorithm when they program it. This may sound sad, but that is true in the general case. In many cases, programmers are not experts in the domain of the problem that the program is trying to solve. It may be a database problem, and you can actually play a lot of tricks if you understand the domain, but the programmer may not know a lot of that tricks. It may be a genomics problem, and you may actually play a lot of tricks. Again, it may be a machine learning problem. You may actually be able to play a lot of tricks to reduce the synchronization, for example, but if you don't know the problem really well, you may not be able to reduce the serialization that you cause because of your poor programming, let's say. Okay, and then even if you have enough domain-specific knowledge to do good parallelization, there's variation in hardware platforms. Each platform is different. Each platform has different strength of cores. Each platform has different communication and locking mechanisms. So whenever you improve performance, it may for one platform, it doesn't mean that the performance will improve for another platform as well. And the question becomes, of course, now, on how many platforms is your application going to execute? And is the programmer going to optimize the application for every possible platform the application is going to execute? That's not an easy problem, clearly. As a result, parallel programming is hard as well. This is one of the reasons why parallel programming is hard, because of the diversity of platforms. And on top of this, there are limited resources. It's hard enough to get the parallel programs correct to begin with. Making them high performance becomes even harder, basically. And programming resources are limited. Programmers are perhaps the most limited resources in the world, especially expert programmers who can do this sort of parallelization. And on top of that, that exacerbates the problem is when you try to optimize the performance of a parallel program, you get into potential bugs, meaning you reduce the critical section size. Maybe you did something wrong, right? Maybe you forgot to protect some variables that are supposed to be protected because they're shared. And this is very easy to get into actually in parallel programs because there's a reason why programmers wrote a parallel program the way it is in the first place. They basically were not comfortable potentially reducing the size of the critical section. Why? Because they thought, okay, I need to protect all these variables. Maybe they were conservative, yes. You can reduce the size of the critical section by reducing the things that you protect, reducing the amount of code that is not supposed to be in the critical section, for example, because it's really not dealing with shared data. But while you're doing that, you may actually be incorrect also, right? Potentially, you may miss some locks. You may make the locking mechanisms more complicated. You can get into deadlocks potentially. You can get into live locks. So basically, as you try to optimize your multi-threaded program, parallel program, you get into a very fundamental performance debugging trade-off. As you try to improve performance, the probability of getting bugs in your multi-threaded programs increases. And these bugs could be simple synchronization bugs. You forget locking something, right? That's important. Or it could be you use a lot of locks you do a lot of fine-grained locking to reduce the probability of conflict between the locks, meaning you reduce the critical section contention, but then you may run into deadlock issues because you locked things in some order that in some cases, and you forgot to unlock things in the same order potentially, right? And you can also potentially get into live lock issues as you increase the number of locks that you're dealing with, and you forget to release the locks potentially, right? So all of these are real problems why programmers may not be able to easily improve the performance of these multi-thread applications. So MySQL is a great example, for example. Database applications are actually some of the parallel applications that people have invested a lot of programming time into. And even in those applications, you run into these bottlenecks, these serial bottlenecks, or these bottlenecks that you see in the parallel portion. Why? Because it's hard to actually improve performance in these multi-thread applications. And also, even if some companies who are quite rich actually throw a lot of programmers into this problem, throwing a lot of programmers could be a solution. But if your programmers are not experts, are not exactly really proficient in terms of what they're doing, then they may actually be causing bugs as well. So unless you have really expert programmers who know how to deal with this sort of stuff, it's going to be hard to overcome this performance debugging trade-off. And it's hard to solve these problems, basically. Basically, I think my point is that you need some help from the hardware that mitigates the programmer effort. Over time, maybe over decades, for example, programmers may learn how to make a program much higher performance while keeping it correct, right? But that takes time, basically. But then what are you going to do if you want high performance immediately or quickly? That's where the hardware support or system support comes in. And that's where programmers' life can become much easier if hardware or the system provides some support to shorten these serial bottlenecks without requiring any or while requiring little effort from the programmer. So that's the idea, basically. So we would like to accelerate these serialized code sections by automatically shipping them to some asymmetric parts of a system. Again, in this particular case, we're going to use asymmetric multi-core. But again, you can think of automatically
customizing an FPGA to actually accelerate these critical sections, right? That may sound like a dream right now, but why not, right? All research starts with dreams in the end. Okay, so now let's go into the next steps. Any questions so far? Okay, I assume people here have done some parallel programming. How many people have done some parallel programming? Okay, I see multiple hands. Do you think parallel programming is easy or hard? Who says easy? Okay, I don't see any hands. Who says hard? Okay, I see all the hands basically at this point. And I also see someone saying hard basically in Zoom. So nobody said easy basically. That I think is proving my point as well. And I don't think you will find many people who say it's easy, unless it's one of those expert programmers who have a lot of experience basically on this topic. But even then, they need to be very careful. Okay, so basically this one example that we're going to cover is accelerated critical sections. In accelerated critical sections, the idea is to design a hardware-software cooperative mechanism. And this mechanism ships critical sections to a large core, a large powerful core that can potentially execute these critical sections much faster than a simple core. That's the idea basically. And there are multiple benefits to this actually. It's not just accelerating faster, accelerating this part. It reduces serialization due to contended locks because of acceleration. It reduces the performance impact of these hard to parallelize sections. And programmer does not need to heavily optimize the parallel code, hopefully. Meaning programmer can say, oh, okay, I'm not going to optimize my code that much. I'm going to make it correct. And I'm going to make it beautifully correct, let's say, so that other people can read it and optimize in the future. Hopefully this will lead to fewer bugs and improve productivity over time. So this sort of acceleration can have benefits that we cannot quantify easily as well. And I believe this is important because a lot of the parallel programs actually are hard to read, hard to maintain. Why? Because they were written to be high performance. And as a result, they're more bug prone. Even if they don't have bugs currently, they may be bug prone if someone else, let's say, goes and improves them, right? And that leads to productivity loss when you have teams improving programs. So basically this sort of idea has benefits that are much harder to evaluate than just performance and energy, scalability, etc. And it's good to keep that in mind because these benefits are actually tough to evaluate in general. Like how do you improve software productivity, right? But you can make intuitive arguments, I think, in terms of why software productivity would improve if you actually give a mechanism that magically or automatically accelerates these hard to improve program portions. Okay, so let's take a look at how accelerated critical sections operates. I gave you the key idea, so it's going to be hopefully easy to understand. Basically, we have an asymmetric multi-core system that looks like this. One core is a large core in this particular case, and large core hopefully executes single thread much faster. We're going to add a critical section request buffer into this large core, such that the critical sections that are encountered by the small cores are sent to this large core. That's the idea, basically. You can think of this as a remote procedure call that's implemented on a single chip. Basically, as we discussed at some point, you have a multi-core chip, and multi-core chip is like a distributed system. And when you get to a system critical section call, that call gets shipped to a large core that can execute that call much faster. It's very similar to a remote function call, if you will, except it's going to be executing on the same chip on a large core. You can also think of these small cores as clients and the large core as a server. Large core is the server for executing the critical sections basically right now. Okay, any questions? I'm going to go into the mechanism now. Okay, now let's take a look at this mechanism. Let's assume that all of the cores are executing this critical section or program that includes this critical section. You can see that the critical section is demarcated by enter critical section, leave critical section. And we want to insert into this priority queue, which happens to be a shared data structure in this critical section. And as I said, we added this critical section request buffer. And let's say processor 2 encounters a critical section, executes this enter critical section call. And at this point, processor 2, instead of executing this critical section, it sends a critical section call request to this critical section request buffer in processor 1, large core. Processor 1 executes the critical section, assuming that there are no other critical sections waiting for execution, because processor 1 serializes the critical section so that it can maintain correctness clearly. And then once it's done with the critical section, it sends a down signal so that processor 2 can continue execution. That's the idea, basically. It sounds very simple. And again, it's very similar to a remote procedure call that you execute on a distributed systems programming. Okay, let's go into a little bit more detail right now. So basically, this is what happens in the small core, right? The small core does some computation, and then it locks some variable, and then it executes the critical section. It unlocks the variable, gets out of the critical section, and prints the result in this particular case, right? You can see the dependencies over here. It computes some data that gets supplied into the critical section, and the critical section gets executed, produce a result, and that result gets printed over here. So this is what we're going to do. Small core, what it's going to, because the small core and large core is sharing memory, they're sharing memory with each other. It's first going to push the input to the critical section on the stack, and then it's going to start a critical section call to the large core with X as the variable. That's the identifier of the critical section, basically, and the target PC as the start of the critical section. That's the PC of this result, basically. So this critical section call request gets sent over the interconnect. So interconnect needs to carry a message saying send the X target PC, the stack pointer that the small core has, and the core ID so that you can return the critical section down signal. And then this request gets queued in the large core. It starts waiting in the critical section request buffer. And at some point, when it becomes the oldest entry in the critical section request buffer, the large core takes that entry, which includes this information that was sent, and basically starts executing with the program counter at target PC, basically, which is the beginning of the critical section. It first acquires the locks to maintain correctness in the system, just to make sure, because some other core may be acquiring the lock, who knows, right? And then it's going to pop the stack so that it gets the input variables. And then it executes the critical section code, and it pushes the result onto the stack so that the small core can actually read it, and then releases the lock, and then it executes a critical section return instruction, which basically sends a critical section done response to the core ID that generated the execution of the critical section. And then the small core basically pops the result that was generated by the large core from the stack, and then prints the result. So basically, the communication happens between the small core and the large core through the stack. You can optimize it, of course, by doing passing registers, etc. If you share the registers between small core and large core, we don't do that here because stack is a very clean way of doing this communication. And then you can see that the critical section execution remains essentially the same as in the small core. So there are no correctness problems in this particular case, but you can potentially optimize the performance, as you can see. And hopefully, the critical section execution on the large core is much faster because this critical section function executed much faster. As a result, the performance of the critical section improved, and performance and the scalability of the application also improved. Okay. Any questions? Okay, there's one question on YouTube asking, do you think compilers have a role to play in creating performant parallel programs? Right now, it pretty much depends on hardware and programming languages. And I think, yes, actually, compilers can actually ease the life of the programmer a bit. For example, I will give an example from this accelerated critical section. So programmer can do all of this that I mentioned, but a compiler can insert all of these calls also to make life easy for the programmer. So everything that I described so far can be done by the compiler, as long as programmers clearly demarcate the critical sections. That's the key, basically. Programmers need to obey some disciplined parallel programming so that critical sections are clearly demarcated, so that the compiler knows exactly what it should and it can actually convert into this remote procedure call. If the programmer doesn't demarcate the critical sections, if they play some tricks, different sort of tricks, they don't use library calls, for example, to do the critical sections, it may be very difficult to identify critical sections, right? Because they may actually use any sort of instruction sequence to do locking, for example. And if they do that, then it may be very difficult for the compiler to analyze the code and without any doubt, perfectly correctly say that, oh, this is a critical section and this is this critical section, right? So it's very difficult for the compiler to do that. So disciplined programming using parallel programming libraries and locking libraries is actually a must, I think, to enable compilers to analyze the code and help the programmers. So there needs to be some effort from the programmer side, there needs to be some effort for the compiler side, and there needs to be some effort for the from the hardware side, as we discussed in the accelerated critical sections. Okay, so let me talk about one problem with accelerated critical sections. If you only have one large core, and if you ship all of the critical sections,
you can cause false serialization. What does this mean? You can have independent critical sections. For example, a core may be executing critical section A, another core may be executing critical section B, and if these execute in independent cores, they execute perfectly independently because they're completely different critical sections. They don't share any lock, right? But if you ship all of the critical sections to a single core, if it's a single core, then these get serialized in the critical section request buffer, right? Even though these are for completely different critical sections, you serialize. This is not a good idea. Either you should execute them on different large cores, or not ship them to the large, not ship one of them to the large core, basically, right? That's the idea. Or maybe use simultaneous multi-threading in the large core so that you can simultaneously execute two critical sections that are independent of each other, right? Now, of course, there's a downside to that, because if you simultaneously execute two critical sections in the large core, you may not get high performance or as high performance as you want for either of the critical sections, okay? So the solution that's employed in this paper for false serialization is called selective acceleration of critical sections. This is one potential solution. Basically, the large core in the critical section request buffer keeps track of false serialization. How many times have I falsely serialized a critical section that could have executed if it remained in its small core? So let's take a look at this. This is our critical section request buffer. These are requests coming from small cores, and large core actually picks those requests and executes them, right? And let's say this is our saturating counters to track false serialization. How many times did I falsely serialize critical section A versus critical section B? Because I know what critical sections are coming. A critical section call request comes to A, I execute it in the large core, so it's not falsely serialized. Another critical section call comes, it's not falsely serialized because it's behind a critical section call for A. All critical section calls for A should be serialized behind each other clearly. But now a critical section call to B comes, and it gets serialized. Unfortunately, this is false serialization. It should not have been serialized because clearly large core starts executing critical section A, and it doesn't have bandwidth to execute critical section call B. So now we increment the counter for false serialization. If that counter becomes higher than a threshold, we basically tell the cores that send critical section call B, don't send us critical section call B. Execute them by yourselves, because you'd be better off executing them by yourself. Makes sense, right? This reduces the false serialization. And how do you determine the threshold? Is of course a function of how fast you can execute the critical sections and how much serialization you cause. So it's a cost benefit trade-off in the end. And the paper discusses that issue, and you can take a look at it. Okay, so if there are no questions, then I will discuss the trade-offs before I go into performance results. So go ahead. There are multiple questions, so please go ahead.
Yeah, I just had a question.
Sure.
What happens when the request buffer ends up being full? Is the request immediately sort of executed in the smaller core?
Yeah, so that's a good question. Basically, what happens is you send a NAC signal, and there are multiple options. I think in this particular case, we basically tell the small core to resend it, for example, after some point. But you can also execute in the small core, right? You can potentially do that because we maintain correctness, right? We do the locking in the large core as well as the small core. We never basically, if the small core gets the lock and the large core wants the lock, large core will not be able to take the lock. So there is no correctness issue. But there may be performance issues in terms of how you deal with it. The paper analyzed this case and discussed it a bit, but there could be better ways of handling it, frankly. Does that make sense?
That makes sense. Thanks.
Okay, sure. There was another question in the back. Please go ahead.
Yeah, just wondering, by passing argument on the stack, does it make use of the shared cache, or it will go through the DRAM?
Yeah, excellent question. Basically, if there's a shared cache, it makes use of the shared cache for sure. Yeah. And in this case, we do make use of the shared caches because there are shared caches on chip, right?
And that makes sense.
Yeah, as a result, that communication is much faster internally. And we will talk about that sort of communication later on in this lecture also, because that communication becomes important actually.
Okay, get it. Thank you.
Okay, great. Okay, very good questions. Okay, so let's talk about pluses and minuses. As with any idea, this idea also has pluses and minuses, right? Clearly, we get hopefully faster critical section execution, not guaranteed, as I said, but hopefully it's faster because it's a large core. But you also get another benefit. Shared locks stay in one place. meaning the large core, assuming that everything executes in every critical section executes in the large core. You are not bottlenecked by our critical section request buffer, for example. By the way, to answer your question in a little bit more detail, a critical section request buffer doesn't need to be, it's not a system bottleneck. So it can be as large as you need it because it's a FIFO queue, right, in the current design. So it's not that bad in terms of design, so you can make it large. As a result, shared locks stay in one place, so you get better lock locality because shared locks stay in the caches of the large core. And hopefully large core has large caches as well, right? So you get benefits on better lock locality. And equally or even more importantly, shared data also stays in large cores, large caches. So you get better shared data locality. So whenever you have updates to shared data, all of the updates remain in large cores caches. They don't need to move between small cores caches. So you eliminate the effect of ping-ponging of the locks as well as shared data. And that is a big effect in terms of the performance improvement, basically. It's not only that you're accelerating execution, you're getting better lock locality and better shared data locality by, in the ideal case, you're getting zero movement of locks and shared data because nobody else other than the large core is executing the critical sections, right? And these are important, I think, as we will see in the results also. The paper actually analyzes these effects if you read the paper. Okay, but of course, everything comes with minuses as well. Now, what we do is we dedicate the large core for critical sections, in this particular case, to ensure that critical sections actually get, to reduce the management overhead of the large core. Clearly, this leads to reduced parallel throughput because you could have dedicated some number of small cores for more parallel execution instead of having a large core that's dedicated for critical sections, right? Okay, but clearly that's a minus, but that minus will reduce assuming that you have many, many large cores in the system, right? Or many, many cores in the system. You have critical section call and critical section done, control transfer overhead. Basically, all of the transfer overhead you need to set up the large core and also return the response. Clearly, this is important. And we will see that this is a trade-off, basically. This trade-off, shared locks staying in one place overcomes this trade-off of critical section call and critical section done signals. And I will mention that in a little bit. And finally, thread private data now needs to be transferred to the large core. So shared data stays in the large core, no problem with shared data movement. But now thread private data that would otherwise stay privately in thread's core, now that needs to be moved to the large core, right? Remember the push that we did on the stack and the pop that we did from the stack? We get worse private data locality in this case because we're moving the private data. And this becomes interesting, as we will see. This has led to some other work that we will discuss. Okay, let's examine these trade-offs. Clearly, these are trade-offs, right? We get basically fewer parallel threads because we dedicate one large core to execute critical sections. We could have used that to actually have more parallel threads, but we accelerate critical sections. So that's an interesting trade-off. Accelerating critical sections usually offsets the loss in throughput in parallel threads, as we see in our results. And also in the future, as the number of cores or threads on chip increases, fractional loss in parallel performance decreases. Meaning, okay, today, for example, you have 16, a unit, an area of that's equivalent to 16 small cores. You dedicate 4 of those small cores to a large core. Basically, you lose 1/4 of your throughput, right? In that case, it's 75%. That's kind of a lot, right? But in the future, you may have 100. You may have an area that's equivalent to 100 small cores. And let's say you dedicate an area equivalent to 8 small cores to a large core. 8 out of 100 is only 8%. It's not 25%. So basically, fractional loss in parallel performance decreases, as you can see, right? And also you can play tricks like using multi-threading in the large core, but of course that reduces the acceleration in the critical sections potentially. I'm not going to get into that right now, but we will cover that in a later work. So, and also the increase, as the number of cores or threads on chip increases, there's increased contention for critical sections, which makes acceleration more beneficial as well, which is interesting. Basically, this problem becomes more important as your contention for locks increases. Okay, so that's the first trade-off. The second trade-off is overhead of critical section call and critical section done versus better lock locality, right? And it turns out accelerated critical sections avoids ping-ponging of locks among caches by keeping them at the large core. And this turns out to be a good trade-off. Yes, the overhead of CS call and CS done signals that you need to communicate, but better lock locality actually trumps the overhead. Why? Because if you think about ping-ponging, it's really bad, right?
assume that you have 16 small cores, and each small core gets to the critical section, and each small core basically gets to the critical section as similar enough times. They both want the lock, and basically they need to read the lock, and somebody updates the lock, and they need to basically coherence mechanism invalidates all of the locks that are in shared caches. So they need to reread the lock again, and they need to update the lock again. So basically you run into this read, update, invalidate loop, if you will, in each core, where you keep reading the lock and reading the lock and reading the lock, and the lock gets ping-ponged across caches. Right? Basically, you eliminate that ping-ponging effect nicely by keeping the lock in the shared cache or small or even L1 cache of the large core, and that lock doesn't move anywhere else. It's worth having a CS call and CS done signal coming from the small cores to keep this lock locality. Okay, and then the last interesting point is we get more cache misses for private data versus fewer misses for shared data. And now this becomes interesting, right? This becomes a good trade-off if the cache misses for private data is lower than cache misses for shared data to begin with. And now this becomes a question to you, perhaps, right? How many, which intuitively, do you think you will get more cache misses for shared data, or do you think more cache misses for private data? Who says shared data? Whenever you're executing a parallel program, do you think you'll get more cache misses in a thread for private data or shared data? Okay, any questions? Like any answers? I think I saw a hand saying shared data. Intuitively, I would think that way also. If your program is optimized, you should not really manipulate private data in your critical section, right? Unless it's an input to your critical section. And ideally, well, not ideally perhaps, but you would expect that shared data would be larger. I will motivate this intuitively. Let's take a look at this priority heap, priority queue, right? Basically, this is from a benchmark that we're benchmarking. It's a puzzle game, basically, parallelized. Basically, what you're doing is there's this heap workload, and we want to update that workload by adding new subproblems, basically adding a new node to the heap. Shared data is the priority heap, essentially, that you're protecting. Private data is the input that you're adding to it, right? Because that's generated by the thread privately. It becomes shared later on, clearly. Okay, as you can see, as you will see over here, okay, sorry about that. As you insert this private data, you need to traverse the tree or heap in this case, which is a tree, as you can see, binary tree in this case, right? And you can see that you will touch 1, 2, 3, 4, 5, the blue blocks in this particular case, essentially 1, 2, 3, 4, 5 blocks to insert one private data block. And assuming that these are not in your cache, and these are ping-ponging, etc., and these may not be even touched for a while, you need to go to DRAM, you get cache misses on all of these 5 blocks, right? And you get cache miss potentially only on this block, and you may not even get a cache miss over here, right? So basically, intuitively, I would say that private data is smaller than the shared data in applications like this. Of course, with finer grained locking, you can reduce the shared data you touch also, but fundamentally, finer grained locking has some other overheads as well. So usually, if in a well-optimized program, you would expect shared data to be larger than private data. So basically, this is a good trade-off. But that's not always the case. The paper actually analyzes this trade-off, and the paper shows that in some applications that are not very well optimized, private data is larger than shared data. Okay? So basically, cache miss is reduced if shared data is greater than private data, because we're converting shared data, the cache misses due to shared data, to cache misses due to private data in this particular case by doing accelerated critical sections. And private data cache misses can be solved as well, as we will see later in this lecture. Because if you think about private data cache misses, it's a communication miss, right? What you're doing is you're communicating an input value from a small core to a large core. And you can actually guess what you're going to communicate before you communicate it. Meaning you can actually push that data that you're going to communicate to the large core before it's needed by the large core. And we're going to talk about that idea, basically. It's going to be the idea of data marshalling. If you can guess what you're going to communicate earlier, and you can push it to the large core, you can reduce the cache misses on the large core side. It's very hard to do this for shared data. For shared data, the misses are not communication misses, right? The misses are really, you need to update this data structure, and data structure has some structure, and you have no idea what that structure is before you start traversing it, right? Of course, I mean, you can imagine mechanisms to traverse it beforehand, but with the dynamic updates from many threads, that structure may change significantly, right? So shared data is fundamentally very different from private data, and handling private data misses is fundamentally easier than handling shared data misses. I think this is at the core of parallel programming as well. So it's good to think about this a little bit. And we will get back to this in the later parts of this lecture. We propose a mechanism that reduces the private data misses on the large core. Okay. Okay, if there are no questions, then I'm going to give you results. Okay, there's one question. Please go ahead.
Yeah, just make sure I understand what you mean by moving locks. Is it like, so say there's two threads that are sharing a cache. So what would happen is, and they're also sharing a lock, I guess. So the lock would come from DRAM into their shared cache. And then what it means to move the lock is then for core one, then to like take it from the L2 shared cache into its L1 cache. That would be moving the lock, right?
Yes, exactly. I mean, either from the L2 shared cache or from the coherence mechanism in L1, right?
Right. Oh, yeah,
we're going to talk about cache coherence in the next week, so you will see it more, of course. But coherence mechanism can supply that data as well.
And I guess that would be, so like doing it this way would be faster than bypassing the cache and going directly to DRAM each time to fetch the lock.
Yes, absolutely, absolutely, because DRAM is way too slow. And if you do that, now you have contention in DRAM as well.
Okay, thank you.
Yeah, very good. Okay, so there's one question on YouTube that I will handle. I think this is related to what we discussed on cache block bouncing, right? Ping-ponging. If that's the bottleneck, basically, if the system is bottlenecked by cache block bouncing, a large core might not be required to benefit from isolating the critical section and link to a dedicated core, right? Well, I think a large core helps in that case, basically, because you keep the locked data in the critical section. You keep the locks as well as the shared data in the caches of the large core. Basically, you eliminate the cache block bouncing problem or cache block ping-ponging problem from the system. So basically, your performance improves immediately because you eliminate that problem. So if your bottleneck is really that cache block bouncing, then actually moving everything to a large core, every critical section to a large core helps that problem and shifts that bottleneck. Okay. Okay, now let me give you some performance results based on this paper. So basically, we're going to compare it to symmetric multi-core, conventional locking. We're going to compare it to asymmetric multi-core, which executes the MDAL serial parts in the large core, but not the critical sections. And then we're going to look at ACS performance, and where the large core executes not only MDAL serial parts, basically when only one thread exists, but also the critical sections, okay, as we discussed, including the forced serialization, etc. And these sort of experiments are not easy to do, actually. This requires a lot of infrastructure building for simulation, because you cannot do this in real systems today because you require changes to the core, etc. And in the past, when we were actually proposing these ideas in 2007, there were not even heterogeneous multi-cores where you could even imagine doing this on real systems. So basically, we built a simulator, a multi-core x86 simulator. We're going to look at one large and 28 small cores. And we have an aggressive memory system. We're going to look at 12 critical section intensive applications from multiple different domains: data mining, sorting, databases, networking, web, etc. And you can see the parameters of the large core versus small cores, similar to what I've shown you in the last lecture. Basically, large core is out of order. By that time standard, it's a pretty strong out of order core, but small core is in order. And we fix the frequency to be the same so that doesn't become an issue. So basically, the gains are really microarchitectural and not due to frequency over here. And you can see there are shared and private caches over here, and there's a interconnect that's bidirectional ring. So interconnect is actually important. If you actually have better communication between the cores, better interconnects, you can actually do this shipping of the function from one core to the large core much faster. Right now, we actually assume a not so great interconnect. It's a bidirectional ring. Basically, you have 5-cycle hop latency. So if the large core that's communicating with the small core is a bit far away from the large core, it takes some time to actually communicate the critical section. So if your interconnect is much stronger, the performance benefits actually are expected to become much stronger. Hopefully, we will talk about interconnects in the coming weeks, and you will appreciate this more. But a bidirectional ring essentially is a ring, right? Cores are on ring stops, and one core may be far away from the large core, depending on its location on the ring. Okay, so let's take a look at the results. These are some key results. Basically, we're going to look at equal area comparisons. In this particular case, chip area is equivalent to 32 small cores. Clearly, symmetric multi-core has 32 small cores, and asymmetric multi-core has 1 large and 28 small cores. And we're going to divide the workloads into coarse-grained lock workloads and fine-grained lock workloads. Coarse-grained lock workloads are essentially, you could think of them as relatively less optimized code. And fine-grained locks are where the code is more optimized, basically more, let's say, parallel programs are more optimized so that the locking overhead is reduced as much as possible. Well, for some definition of as much as possible, right? And we set the number of threads to the best number of threads. So to do the comparisons fairly, for each application and each system, for a given application has a best number of threads to execute on a given system, right? Basically, we set that number of threads to do the comparison points. For example, one workload may execute on the SCMP, may get the highest performance with 16 threads. So we look at that performance for that workload. The same workload may get the best performance on accelerated critical section system with 28 threads. We look at that performance and we compare those two performance levels because that's what makes sense, right? It doesn't make sense to compare the performance levels of a given point, 32 points. We will see those results because some particular system and workload may not be very efficient at that point because of the scalability curve that we have seen, right? Okay, so these are important things that you need to keep in mind when you're doing multi-thread execution evaluations. You should be fair, basically, to each system and each workload. Okay, let's take a look at the results given this. You can see that the performance improvements are quite significant. So what is the cyan bars or turquoise bars? These turquoise bars are accelerating sequential kernels, meaning sequential part is executed in the large core. Accelerating critical sections, basically both sequential part as well as the both MDAL serial bottleneck as well as critical sections are executed on the large core. So basically the ACS benefits are the benefits of the blue bar compared to the turquoise bars over here. And you can see that overall the performance benefits are quite significant, especially in coarse-grained locks. You can see that the performance benefits are very high with accelerated critical sections. Accelerating the serial part is very high in some workloads, so which means that serial portions are bottleneck in some cases, but critical sections, accelerating critical sections on top of the serial part actually buy you a lot of performance. As expected with fine-grained locks, performance benefits are lower, but they're still there because there's still some contention for locks, especially with large number of cores like 32, right? But in some cases, actually, you reduce performance due to loss of throughput and you don't gain as much performance. This is spec JBB, for example. But this actually improves as you increase the number of cores to 64 and 128. So overall, the performance benefits are quite significant. You get 40% higher performance improvement compared to symmetric CMP and more than 30% performance improvement compared to asymmetric CMP. Okay, and these are the scalability curves. So these are the full results, basically. You can see the scalability curve for each benchmark, basically speed up compared to a single thread execution, compared to a single small core execution. And you can see the scalability curve for symmetric multi-core, asymmetric multi-core, and accelerated critical sections. So you can see that, let's pick one workload, for example. This PageMine is one workload. You can see that the scalability curve shifts to the right, meaning the performance saturates at higher number of threads. But still, even with accelerated critical sections, performance starts degrading after some number of threads. Basically, accelerated critical sections doesn't help all of the bottlenecks in this particular case, right? There are other bottlenecks in the system. And maybe there are bandwidth bottlenecks, for example, right? So there are some other workloads where accelerated critical sections actually keeps improving scalability as you keep adding more threads. The puzzle workload, for example, whereas ACMP and SCMP are not that good. As you can see, the performance saturates at 2, which is very low for 32 threads. But here you go up to 6, for example. And here again, you have similar examples. Basically, scalability improves on 7 workloads out of 12 in this particular case. And you can see that some workloads are more scalable and some workloads are less scalable than others. For example, in this workload, spec JBB, the scalability is very low to begin with, right? The speed ups are actually up to 3, which is very low, right? On some other workloads, scalability is good to begin with. This traveling salesman problem, for example, scalability actually goes up to, let's say, 13 over here. But accelerated critical section is actually better than other workloads. Okay, you can see more analysis in the paper, but basically the takeaway is the performance as well as scalability improves. There's no energy analysis in the paper, but actually energy improves as well according to our later results, much later results, because energy is always a function of performance as well as how much waste you have. Here, we're improving both performance as well as the waste in the system, meaning the data movement bottlenecks, right? The ping-ponging bottlenecks. As a result, energy actually improves in the system. Okay, now we would like to generalize the idea. So this is for accelerating critical sections. The question becomes, can we accelerate all bottlenecks or critical paths by executing them on a powerful core? And that's what we're going to discuss next. But this is the paper we discussed, and if you're interested, you can take a look at it in more detail. Any questions before I move to generalization? Okay, there's one question. Please go ahead.
Yeah, the first question is the reason why you had a large core be the same frequency as the smaller cores because you wanted to be conservative, because adding more microarchitectural mechanisms is less costly than adding frequency, and while adding frequency is just the easy way to get more performance?
Yes, exactly. Basically, we wanted to be more conservative. We wanted to not, we wanted to not cause the issue that people may think that the benefits are coming from higher frequency, right? Basically, the benefits are coming from microarchitectural effects in this case, as you can see.
Okay, I guess this is less specific to the paper, but is there do you know, or what are some examples of places where they've used heterogeneous cores? Because I was just thinking that, because there's that trade-off, right, between you lose throughput if there's no shared critical section. So like if in like for a general consumer case, I can easily imagine where each core on the thread is just doing a completely separate task, and none of them are sharing any bottlenecks. Yeah. And so on average, the performance might be worse.
Yeah. I mean, this goes back to your question on multi-programmed versus multi-threaded, right? I think yesterday we discussed this. We're going to get back to it, I think. But again, if you're running, if you're running a multi-threaded application, and if you care about its performance, this makes sense, probably, right? But if you have multi-programmed applications, then you have a trade-off, right? We accelerate a limiting bottleneck potentially from one thread, or do you accelerate some other application, right? And we're going to discuss that actually. A later work will tackle that issue. So I think if you really want to make this very general purpose, you really need to tackle issues like you discussed. No question about that. If I interpret your question as if people are using this idea in existing heterogeneous multi-core systems, then I don't know the answer, frankly, because clearly we have heterogeneous multi-core systems right now. Apple, for example, has large versus small cores. I'm not sure if they're using it for this particular purpose. They can, right? There's no reason why they cannot in their system. But again, they don't disclose how they use their cores in any of their systems.
Okay, yeah, thank you. I think it must be a pretty complex problem. Like maybe for Apple, they find that people spend 50% of the time on the cameras, and then on the cameras, I guess the improvements they get by pipelining the advanced stuff they do underneath the scenes from the large core would outweigh any kind of downsides during the normal non-camera usage of the phone.
Yeah, I mean, potentially, we don't know exactly, but I would expect critical execution, like execution that would benefit from high performance, potentially critical sections. It could be some other thing that is critical, right? As we will discuss next. Makes sense to execute on the large core, right? It doesn't make sense to waste the energy of the large core on non-critical tasks, right? And critical may be critical sections, critical may be something that's really important to the user at that point in time, right? Interactive, so that you actually handle it very quickly. So yes, I think the general thinking is very similar. Even though we look at the specific case of critical sections here, I think criticality in general should be defined such that it's critical enough to be executed with a powerful core, right?
Yeah, thank you.
Yeah, sure. Okay, no more questions. So I'm going to basically go to the next thing, basically. So basically, accelerate critical sections. Is there a question in the back? Okay, go ahead, please.
So I found this is a really interesting idea, but what do you think of implementing it in the operating system? So as far as I know, the operating system have a global view of the cores and can decide which code to run on which cores. So if you have two large cores, then you can, by allocating different locks to different cores, you can avoid the forced serialization. And also, when a program tries to grab a lock, I would assume that the OS will do some context switch in case the lock is not available. So, I mean, there are already some mechanism in the operating system. So would it be easier or maybe more, can be more easy to be adapted if implemented in the operating system?
Okay, so let me tackle parts of your question. First of all, if you have 2 cores, yes, certainly you can reduce false serialization by sending independent critical sections to different cores. But you can do that in hardware as well, right? You can certainly do that in the runtime system. So in terms of locking, it depends on how you do the locking, right? In many parallel applications, you really don't want to go through the operating system to do your locking, right? You want to communicate through memory, and then you want to ensure that basically you don't do a context switch when the lock is not available. You just wait. You just do busy waiting in the parallel, because hopefully the lock will be available soon, and the parallel application may yield, of course, right? If you do a yield in the thread, then you actually, if you go to sleep, for example, then you basically yield your turn and somebody else can get scheduled. Sure. So I would say that locking should not be managed by the operating system in general, unless the application gives control back to the operating system. That's how you get the highest performance. So it's more user level parallelism, basically, that you're exploiting, and user level management of the parallelism. That said, I think you have a point. Maybe things should be managed by the runtime system, right? There's some user level runtime that can actually manage things nicely, and that's, I think, in line with the thoughts of this paper. Basically, there's some user level runtime that can do the resource allocation potentially, and it's synergistic with the ideas proposed in this paper for sure. Yeah. And actually, there is a paper that was published after this work, maybe a couple of years. I don't remember the name of the paper right now, but somebody implemented exactly the same idea, accelerated critical sections, on a user level runtime library. It was an ASPLOS paper, I think, if I remember correctly. I have to find it. Maybe one of the TAs will find it. But if you search for like critical section server client model on multi-cores, there was a paper that basically essentially did everything that we did completely in software, basically. I don't think they use large cores, by the way. They even use small cores, and they showed benefits. So by shipping even into the small cores, have benefit because of shared data and lock locality, right? You get better locality, and we show that in the paper as well. If you don't basically have asymmetry, you still get benefit because you keep the shared data and locks in a single cache or single level cache hierarchy of the core that serves the critical sections. Make sense?
Yeah, I see. It makes sense, especially the context switch of the operating system. Yeah, I think that's real. Yeah.
Okay, cool.
Yeah.
Okay, great. Okay, now let's basically try to generalize this idea. The question now becomes, can we accelerate all types of synchronization bottlenecks? We're just looking at critical sections, but critical sections are just I don't want to call it a small fraction. It's actually a reasonably large fraction, but just a fraction of bottlenecks. And that brings us to the next work that we did actually along these lines. And basically, here we're going to start with defining bottlenecks. Basically, we already kind of talked about it, but I want to define it more formally, perhaps. Basically, bottlenecks in multi-thread applications are any code segment for which threads contend or wait for, basically. And we've seen some bottlenecks, MDAL serial portions, for example, where only one thread exists. Clearly, that's on the critical path. Critical sections ensure mutual exclusion, and they're likely on the critical path if contended. Barriers ensure all threads reach a point before continuing. The latest thread arriving at the barrier is on the critical path. And pipeline stages and pipeline parallel programs, basically pipeline parallel programs is just to jog your memory. Different stages, a loop iteration is divided into stages, and different stages of a loop iteration may execute on different threads. And the slowest stage makes other stages wait. And that slowest stage is on the critical path of execution of a multi-thread application. And these are different types of bottlenecks that are going to be targeted by this work. And the other observation, perhaps it's obvious, but I think it's good to clarify it, is that limiting bottlenecks change over time. So it's not like we have one lock that's bottlenecking you. These bottlenecks change over time depending on what you do to the data structures dynamically. So let's take a look at a cooked up example. As I say, this is a cooked up example, but you will see very similar examples in real world applications. What we're going to do is we're going to look at two linked lists, A and B. A is full to begin with, B is empty to begin with. And each thread is going to do exactly the same thing. It's going to first take the lock on linked list A, traverse it, and remove an element from list A, and then unlock it. And then It's going to do some computation on X, the element that's removed, and it's going to take the lock on initially empty linked list B, traverse it, and insert into it. And then it's going to unlock it. And each thread is going to do this until A is empty. Basically, we're going to take a look at how the bottlenecks change. So you can see that there are two critical sections, A and B, and there's some computation in between that's non-critical. And if you execute this cooked up application with 32 threads, we're going to look at the execution time, and we're going to look at contention, number of threads waiting for two different locks, A and B. And you can see that lock A is the limiting thread initially, and lock B starts becoming the limiting thread afterwards. And there's some middle point over here. Both lock A and lock B can be limiting threads. Why? Because initially, everybody's contending for lock A because the linked list is quite large. So it takes time to traverse it. So the critical section contention is pretty bad over here. Whereas lock B is easy to get because you keep adding elements to list B, and list B is too small to begin with, right? As list A starts becoming smaller and list B starts growing, the contention bottlenecks actually starts changing over time. And of course, the contention depends on how much computation you do, etc., which we don't analyze here. But the key demonstration is that limiting bottlenecks change over time. So if you want to actually accelerate limiting bottlenecks that are on your critical path, that are making threads wait, then you should actually identify these limiting bottlenecks dynamically online. Okay. Okay. And this is another example from a real world application. You can say that's a cooked up example. I don't believe it. Well, if you see a cooked up example, my suggestion would be to believe it, or at least be open-minded enough to think that, oh, this may actually happen in real programs as well, or something like this may happen. And that actually happens, basically. It's another example from MySQL running some queries, 16 threads. There are two locks you can see. And you can see that the problem is actually even worse. It's in a very fine grain, you see changes in the limiting bottlenecks. Limiting bottleneck is defined as the bottleneck that causes the most number of threads that are waiting. Okay. Okay, and you can actually draw these similar beautiful curves for different applications, and you will see similar curves. It's very interesting to draw them, but basically parallel applications are like this. Okay, so bottleneck identification and scheduling, the key insight here is that thread waiting, basically a thread becoming idle and waiting for some other thread, clearly reduces parallelism and is likely to reduce performance. It's likely to be on the critical path, basically. And code that's causing the most thread waiting is likely to be on the critical path, likely causing your critical path. And the key idea in this paper is very simple. Dynamically identify bottlenecks that cause the most thread waiting. So we're going to basically count the amount of thread waiting each bottleneck causes. And basically, we're going to order the bottlenecks based on the amount of thread waiting they cause and accelerate them. Accelerate the ones that are going to be causing the most thread waiting. In this case, using powerful cores and asymmetric multi-core processor, but you can imagine other ways of accelerating them, prioritizing them in the memory scheduler. Depending on what the nature of the bottleneck is, you can give more cache, for example, etc. There are many ways of accelerating them. You can design a customized core for different types of bottlenecks. You can design a customized reconfigurable FPGA engine. You can design basically different accelerators for these bottlenecks also, which is a direction that we did not pursue. But I think it's also very interesting to pursue these directions going into the future. Okay, but let's take a look at what we have pursued, basically. Compiler, library, and hopefully not the programmer. Programmer hopefully obeys nice principles in parallel programming, and they basically use library code to actually identify and code with critical sections, pipeline stages, and serial parts, parallel parts, as well as barriers. So as long as you use library code, compiler and library can do what I'm going to describe. Nicely defined library code that can be analyzable, etc. Basically, compiler and library annotates bottleneck code and implements waiting for bottlenecks. We're going to talk about that. And it creates a binary containing BIS instructions. BIS is bottleneck identification and scheduling. And the hardware, using those BIS instructions, measures thread waiting cycles for each bottleneck dynamically and accelerate the bottlenecks with the highest thread waiting cycles. So basically, it's a hardware-software cooperative mechanism. And I think it's very difficult to make these mechanisms pure hardware or pure software, or at least to get the highest performance when you actually do pure hardware or pure software. So let's take a look at the compiler and library support. basically, what are the code modifications that we need? So this is a critical section, right? While you cannot acquire the lock, you wait, watching for an address, and then you acquire the lock when the address changes, and then you execute the critical section and you release the lock. To make things easier to analyze, we outline the critical section call just as a library call, right? If you program using libraries, that's what you would do anyway. And then we're going to delineate the call with a bottleneck call instruction. This is a new instruction with a bottleneck ID. This is enumerated by the program, the compiler, basically. And then there's a target PC. Target PC is essentially the body of the critical section over here. And you can see that you need to acquire the lock first, and then you need to watch for the lock and then acquire the lock. And then it ends with a bottleneck return saying bottleneck has ended. These are going to be useful for us to accelerate and keep track of acceleration. Okay, I've discussed these, and that's the body. Now, how are we going to implement waiting? We need to keep track of how much waiting this bottleneck causes. And for that, we introduce another instruction. Basically, instead of having instructions that wait for the loop, we have a specialized bottleneck wait instruction with a bottleneck ID and a watch address. You can think of this as a version of the mwait instruction. There's an mwait instruction that exists in the x86 ISA, for example. Basically, this is a basically bigger version of the mwait instruction that watches an address and associate that waiting with a bottleneck ID, and it counts how long are you waiting for this bottleneck ID. Basically, while you cannot acquire the lock, you're going to increment this thread waiting cycles associated with that bottleneck ID. That's the idea. Hopefully it makes sense. So this is used to keep track of waiting cycles. I'm going to show you an example of this. And these bottleneck call and bottleneck return are used to enable acceleration by delineating the critical sections. Okay, so you can do the similar thing for barriers. So this is a barrier, basically. This is the code running for the barrier, and you return once you finish the barrier. This is the bottleneck call. And here you enter the barrier, and you basically wait unless, if not all threads are in the barrier, you wait. And this is where you wait, basically. Basically, if you're waiting over here, some other thread is the bottleneck. And you need to keep identify that. Okay, you can read the paper for more details. There's some. You need to be careful, basically, how you actually implement these bottleneck call, wait, and return instructions, and how you insert them. And this is the pipeline stages. Basically, you can see clearly that you dequeue the work, do the work, and you basically enqueue the next work. And you may have a bottleneck in the previous stage. If your queue is empty, you're waiting for the previous bottleneck ID, and you're incrementing the waiting cycles for the previous bottleneck ID. If you have a full queue, which means that means that the next stage is the bottleneck, so you increment the waiting cycles for the next bottleneck ID. So all of these bottlenecks need to be treated differently, as you can see, because the nature of how they're bottlenecking and where you should increment the thread waiting cycles is different. And if you come up with another synchronization primitive, you need to come up with how to insert bottleneck call, bottleneck wait, and bottleneck return instructions. Okay, now assume that you've inserted these bottleneck call, bottleneck return, bottleneck wait instructions, BIS instructions. How do we actually use them in hardware? That becomes interesting now. This is our hardware overview. Basically, performance limiting bottleneck identification and acceleration are completely independent tasks. Acceleration can be accomplished in multiple ways. You can increase the core frequency and voltage, which we don't handle over here, but you could also do that. You can prioritize and shared resources. So one of the downsides of the upside of increasing core frequency and voltage is you can, if you see that a core is executing a critical section or a bottleneck, for example, you immediately increase its frequency and voltage, right? The hope is that this will accelerate the bottleneck. It may not accelerate the bottleneck in a microarchitectural way because you're not changing the core type. But if the bottleneck benefits from increased frequency and voltage, you can execute it faster. The downside is that, the upside is that you're not shipping anything anywhere, right? No potentially difficult shipping required. But the benefits may not be as large, right? You don't get the benefit of a larger core in a microarchitectural way. You don't get the benefit of a larger cache, and things stay in a larger cache. Basically, ping-ponging effects all remain in this case, right? So increasing the frequency and voltage may sound like a nice thing to do, an easy thing to do, and it's clearly an easy thing to do. That's why it's done in industry right now. If you know I think Intel called this the thread boost, right, or something like this. Different companies call different things, but certainly this has been implemented by industry. Whenever you have only one core running, for example, you boost the frequency and voltage.
You can do the same thing if you have a critical computation running on one core, basically. That's why this idea is adopted much more easily than heterogeneous cores or some other form of acceleration for critical sections, for example. You can also do prioritization and shared resource, and we saw this in parallel application memory scheduling, right? You can also do migration to faster cores and asymmetric multi-core. You can do all of them at the same time also, potentially, right? All of them can be combined at the same time. You can prioritize the shared resources. In shared resources, the critical section executing on an asymmetric multi-core, while the asymmetric multi-core, while the large core is also has a higher frequency and voltage. But we're not tackling all of those at this point. We're going to look at asymmetric multi-core. Okay, so let's take a look at the hardware right now. How do we measure the thread waiting cycles? So we have some small cores and a large core. And small cores, and we're going to add a buffer over here that keeps track of thread waiting cycles. We're going to call that the bottleneck table. And let's say we get to a bottleneck wait instruction in the small core. That bottleneck wait instruction creates an entry, if it doesn't exist, with the bottleneck ID, and has a number of waiters, which is 1. And it basically has a thread waiting cycles of 0. Now that thread waiting cycles gets incremented as long as small core keeps executing the bottleneck wait function, instruction. So as long as the small core is waiting for bottleneck wait, that thread waiting cycles gets incremented. And if another core starts waiting for the bottleneck wait, the waiters gets incremented by 1, and thread waiting cycles keeps getting incremented by the number of waiters after that, right? Okay, and that's what's happening over here. At some point, small core stops executing bottleneck wait instruction. It notifies the bottleneck table. Waiters gets decremented, and thread waiting cycles continue getting incremented by the number of waiters. At some point, the second small core, or small core 1, also stops executing the bottleneck wait function, and the waiters become 0. That's how you compute the thread waiting cycles. Basically, thread waiting cycles get incremented in this global table while some thread is waiting for that bottleneck, which makes sense, hopefully. That was our intention. And you don't have to do this incrementing by cycle. You can do it in a coarser grain. You can quantize it, etc. We're not going to talk about that at this point right now. Okay, now you have a computation of the thread waiting cycles. How do you accelerate bottlenecks? Let's take a look at what happens. We now in the bottleneck table assume that we have 2 different bottleneck IDs, 4600 and 4700. They have 2 different thread waiting cycles, 100 and 10,000. Let's take a look at what happens. The small core gets a bottleneck call, 4600. It queries the bottleneck table asking, is this a critical bottleneck? And the bottleneck table says, no, your thread waiting cycles for this bottleneck is too small. It's smaller than the threshold. So please execute this bottleneck locally. And the small core says, okay, I'm going to execute this locally. So nothing needs to be done. Now, small core 1 gets the bottleneck call 4700 later. It asks the question to the bottleneck table. Bottleneck table, is this a critical bottleneck? Bottleneck table says, wow, the thread waiting cycles for this bottleneck is quite large. So please prepare and execute this in the large core. And it basically sends an execute remotely signal to the small core. Small core then prepares some packet and sends it to the large core, just like we did with accelerated critical section. It's a very similar packet, basically. But in the large core, we have a scheduling buffer. It's not the critical section request buffer right now. It's a scheduling buffer. It keeps track of the bottlenecks, program counter, stack pointer, core ID, plus the importance of the bottleneck, which is thread waiting cycles. And it's going to schedule the bottlenecks that are the most important, meaning the highest thread waiting cycles first. Okay. And then at some point, it gets scheduled based on that scheduling order. And the paper discusses issues like, okay, how is thread waiting cycles first can lead to deadlock, etc. How do you handle that? And you can read the paper for more detail. Okay, so that's the idea basically. And then, of course, when the bottleneck execution is done in the large core executes the bottleneck return function or instruction, which basically sends a signal to the small core saying, small core, I'm done with the bottleneck execution, so you can continue. And that's the idea basically. So you can say that, okay, this bottleneck table can be large overhead, because now in order to be able to execute a bottleneck, you need to query this table. So what we do is we cache these entries in this table in the small cores using structures called acceleration index tables, such that the small core can quickly ask the question, should I accelerate this bottleneck or not? And of course, you need to keep this acceleration index table coherent with the bottleneck table. So bottleneck table periodically updates these acceleration index tables once in a while. Okay. Or bottleneck table actually updates these acceleration index tables when a bottleneck becomes critical, actually. That's when you really need acceleration index tables to be updated, right? So acceleration index table basically keep track of bottleneck IDs that have to be shipped to the large core. Otherwise, small core assumes that the bottlenecks need to remain in the small core. So that makes the design a bit simpler. The bottleneck table doesn't become a bottleneck, basically, it's in itself. Okay, hopefully that's clear. Any questions? Okay, so basically, I've given you the mechanism for determining thread waiting cycles and accelerating bottlenecks. There's also false serialization issues that happens in this case if you have a single large core. Even if you have multiple large cores, false serialization can happen if you have many bottlenecks going into the large core. So you need to deal with it, and the paper talks about it similarly to ACS. There's preemptive acceleration, which I'm not going to talk about. That's actually quite important for accelerating threads running for a barrier. So you preemptively, ask the small core to accelerate a bottleneck, because small core may not be when you're running for barrier code, when you're a thread that's running for to execute the barrier, you don't know whether you're the lagging thread, right? But the bottleneck table may have this information. So this centralized structure preemptively accelerates a small core that it thinks is the last thread to reach a barrier, or that it thinks it's on the critical path of reaching a barrier. And this is important. We don't discuss this mechanism, but it's very important actually to accelerate barriers. And there's support for multiple large cores as well. Okay, we talk about hardware cost, but you can read the paper for it. Actually, the hardware cost is not that bad for something like this. The real issue is complexity, meaning you need to make sure that everything works correctly. You need to make sure that, so total storage cost, for example, for 56 small cores and 2 large cores is less than 19 kilobytes, which is really nothing, right, in today's standards. The real issue is really making things work, making things function correctly, making things not deadlock, etc., and making sure that you have the large core there, making sure that you have the critical section request buffer functioning correctly. So verification and making it work, validation is really the harder issues, I would say. And there are performance trade-offs that are similar to X-rated critical sections in a sense, right? I'm going to go through this quickly because we've covered similar trade-offs in X-rated critical sections. Here, the trade-offs are similar. You have faster bottleneck execution versus fewer parallel threads. But again, acceleration offsets the loss of parallel throughput with large core counts. You get better shared data locality versus worse private data locality. It's the same issue again. Shared data stays on the large core, which is good. Private data migrates to the large core, which is bad. But we can fix this problem of data marshalling, which we're going to talk about next. You get the benefit of acceleration, but you have the migration latency of things to accelerate, right? Migration latency is usually hidden by waiting, which is good, unless the bottleneck is not contended. So if the bottleneck is contended, meaning that you ship the bottleneck somewhere and you wait in the critical section request buffer, while you're doing that, you migrate the bottlenecks to the large core. So in a sense, migration latency is not on the critical path if the bottleneck is contended. But if the bottleneck is not contended, migration latency is on the critical path. Of course, this is bad. You should not have shipped the bottleneck over there to begin with, but maybe you did not do too bad because maybe the bottleneck is not on the critical path to begin with. But you may actually make a bottleneck on the critical path by shipping it wrongly to the large core, right? And that's a decision that you need to make carefully. Yes, there's a question, I think. Yeah, go ahead.
How exactly do you guarantee that the shared data stays in the large cores if it's the table that decides which is locally executed and which isn't?
Yeah. So basically, that's a good question. It's not a guarantee. It's basically a probability. Probabilistically, shared data stays on the large core for contended bottlenecks. But yes, there is no guarantee, absolutely. You're absolutely right, especially in this case. In accelerated critical sections, even in accelerating critical sections, it was not a guarantee because there was a false serialization mechanism, if you remember. Here, it's also not a guarantee, even less of a probability. But empirically, we find out that shared data on contended bottlenecks and shared locks on contended bottlenecks stay on the large core. And as a result, you get a lot of benefit from that. For non-contended bottlenecks, yes, they don't even go to the large core. But if you're doing your bottleneck identification nicely, and there's a good, nice separation between contended and non-contended bottlenecks, then non-contended bottlenecks don't matter anyway as much. Does that make sense? Okay, great. That's a very good question, basically. So if you really want to guarantee shared data stays on the large core, you should ship all of the bottlenecks over there. Or you should ship the bottlenecks whose data you want to stay there into the large core. And you should do it always. Okay,
Okay, we have a similar evaluation methodology. Again, evaluation in these works is not easy. That's why you don't see a lot of people working on these problems. Even though these are very fundamental, very important problems, evaluation is actually much harder than your regular, let's say, other evaluations that we've discussed so far in architecture, for example, or even systems, right? Basically, you need to really do end-to-end evaluation of real applications, but you need to do it on simulation because these real systems don't exist for this. Okay, and we see, and I'm not going to go through this in detail, but you see, it's very similar evaluation. Large core is essentially the same frequency. Now we have more area that we look at, and we actually have more large cores as well. Okay, now these are the comparison points: symmetric multi-core, asymmetric multi-core, as we have discussed, accelerated critical sections. Accelerated critical sections is applicable to critical sections and serial portions and multi-threaded workloads, but they're not applicable to barrier-based synchronization that don't necessarily have critical sections, right? Or pipeline parallel programs. And feedback-directed pipelining is another mechanism that was proposed in the past. It's a software library that accelerates only slowest pipeline stages. Basically, it monitors at a coarse grain which pipeline stage has the lowest throughput, and it ships them to the large core, for example. It's applicable only to pipeline parallel workloads. So the beauty of this is it's applicable to all of these bottlenecks that we consider. And if you want to consider more bottlenecks, you can basically express those bottlenecks using the 3 instructions that we discussed and program them nicely, and they would be applicable to BIS. Okay, and this is the performance improvement we get. This is one example of performance improvement results with 32 small core equivalents. And you can see that ACS/FTP, which can be used together, by some performance improvement. That's good on these workloads. It's respectable, basically. But this bottleneck identification and scheduling actually buys even more performance improvement. So there are some workloads that ACS is applicable to. There are some workloads FTP is applicable to. And they together provide performance improvement, whereas BIS is applicable to all of the workloads. And there are many workloads where limiting bottlenecks change over time. You can see that. And as a result, BIS actually provides a lot of performance, the analysis in the paper. And also in these workloads, BIS accelerates barriers which ACS does not accelerate and cannot accelerate. And you can see that in some workloads like traveling salesman problem, ACS/SPP is better than bottleneck identification and scheduling, which is not good for bottleneck identification and scheduling. This shows that bottleneck identification and scheduling is not doing a good job identifying the content bottlenecks. And also, it's not getting the benefit of, or full benefit of keeping the shared data and locks in the large cores caches, basically, because it's selectively doing that. Okay, but overall, BIS is a better mechanism compared to prior mechanisms, as you can see in the results. BIS also improves scalability on 4 of the benchmarks. So scalability improves with bottleneck acceleration as well. Now let's take a look at this interesting question. Okay, there's a question. Go ahead, please.
Would the traveling salesman problem potentially fall into a category of one which has a lot of very small bottlenecks, so the table doesn't keep track of them all, and therefore a lot of equally critical sections are offloaded?
Yeah, so that's actually a very good question. I'm not sure. I mean, I don't remember the implementation of this traveling sales problem, but yes, you can certainly program it that way. I think if I remember correctly, this was one of the fine-grained locking mechanisms. And yes, you have a lot of small bottlenecks, and BIS basically doesn't quite identify the correct bottleneck, and as a result, it gets confused. So I think your intuition is in the right direction. I cannot say it perfectly, completely, because I don't remember. It's been a long while since we did this work, like more than 10 years or so. But I believe your intuition is right. And I think your intuition is kind of also seen in this graph that I'm going to show next, where here in this graph, we're showing that fraction of execution time spent on predicted important bottlenecks. So you can see that, I mean, execution time, of course, maximum is 100%. The blue bar is showing how much of the execution time is spent on predicted important bottlenecks using accelerated critical sections and feedback-directed prefetching, meaning how much of the time you're using the large core. And in TSP, you're using the large core a lot, basically almost 100% of the time, but maybe you're not that accurate, as we will see. Okay, well, you're not perfectly accurate, but I think you're not accelerating them, basically. Okay, so basically, using the large core doesn't mean that you're doing the right thing necessarily, right? You should also be using the large core for bottlenecks that are that are actually important. So now let's take a look at what fraction of the execution time that's spent on predicted important bottlenecks are actually spent on actually important bottlenecks. So this is a hard study to do. This requires you to trace back the program from the end of the execution to the beginning to figure out which ones are what is the critical path, basically. And it's not a perfect mechanism because critical path changes dynamically as you accelerate things as well. So it's an approximate result that I'm going to show you. And you can see that the actual critical path is actually reasonably significant. So the green parts of both bars is the actually critical path. So let's take a look at, let's define some metrics. Coverage is the fraction of program critical path that's actually identified as bottlenecks. So in ACS, the coverage is about 39%. This increased coverage to 59%. That's basically how much, how much do you change the green part? The green part, the part that is actually critical, that's accelerated on the large core, increases from 39% of the execution time to 59% execution time, going from ACS to BIS. And that's the benefit of BIS. So coverage increases, coverage of the critical path increases. Accuracy, on the other hand, is the identified bottlenecks that are on the critical path over total identified on the bottlenecks. What fraction of the total identified bottlenecks are actually on the critical path? So the accuracy is actually very similar. Accuracy in this ACS case is the green part of ACS divided by the blue part of ACS, all blue part, and that's 72%. In case of BIS, is green part of BIS divided by the total red bar, which is about 73%, which is very similar. So the accuracy of identification of the bottlenecks doesn't change significantly, but coverage changes significantly. Hopefully that makes sense. So which also means that there's still more room for improvement. Even in this analysis, which is not perfect, because critical path analysis is always difficult to do, you see that there's still room for improving coverage. There's still a lot of room for improving, there's a lot of room for improving coverage. There's a lot of room for improving accuracy. By improving coverage, you improve the utilization of the large core on important stuff. This doesn't mean that bottleneck gets accelerated again, right? Necessarily, because you may be, large core may not be useful for accelerating the bottleneck. So, but at least you identify the program critical path that is actually on the critical path. Accuracy, if you improve the accuracy, then you don't waste the large core on unimportant stuff, right? Basically, this part in BIS is wasted on unimportant stuff that is not on the critical path. Ideally, you ship only the critical path to the large core. And this graph is also important because if you can identify the bottlenecks accurately with high coverage, you can use other acceleration mechanisms, right? So acceleration mechanism is independent of how you identify the bottlenecks. If you can identify them accurately with high coverage, you can potentially use something else. And that's for future work to investigate. Okay, let me give you some scaling results also. Performance essentially increases with more small cores because contention to bottlenecks increases. And also loss of parallel throughput due to large core reduces. We discussed this, but these are some results that actually demonstrate that. You can see that performance improvement with BIS increases. And more large cores, using more large cores actually is helpful. It can accelerate independent bottlenecks without reducing parallel throughut because as long as you have enough cores. So you can see that if you have 3 large cores, the performance actually is the highest. And that sounds good in a sense. Okay, and that's the summary of BIS. I don't want to reiterate all the points that we discussed, but I think the key over here is BIS provides comprehensive finer grained bottleneck acceleration with no programmer effort, assuming the programmer obeys some disciplined, library-based parallel programming synchronization constructs. There's no effort required by the programmer. All of this can be done by the compiler and the library. And as a result, you improve both application performance and scalability. And that's the paper. Any questions? Yes, please go ahead.
So this paper is from almost 10 years ago. Do you know if there's any, this has been implemented in actual processors yet? Or
so I don't know. This is I mean, these sort of ideas are not necessarily exposed if they're implemented because they're part of the. So for example, we discussed the example of Apple, right? The management of large core versus small core is done by completely internally, right? So it may potentially be implemented, but we don't know. But in more open systems, as far as I know, I haven't seen anything, but who knows, right? It's hard to tell.
So no one's ever gonna notify you if ever.
Yeah, exactly. We do not patent the work, so they don't also ask for permissions for the patent. Although this is just publications, basically. So I think that's good for academic research, certainly. But the bad part is you don't ever know if somebody uses these ideas, right?
But in like academic research, has this inspired a lot of follow-up work on?
Yeah, I would say yes. I mean, if you, I haven't checked recently as much, but in the past, this work has inspired a lot of follow-up work in academic research. And as I said, this is a hard area to research on. So you won't see thousands of researchers working on this area. So I would maybe pick on machine learning over here. Machine learning, I would say, is an easy area to research today. Accelerating machine learning, for example. I will pick on it because it's a relatively well-known algorithm, right? You accelerate it, you try different ideas, you try real systems, you try simulators, yes, but it's relatively easy to do. Whereas here, it's a tough area, right? It's a very fundamental area. You deal with synchronization. You need to really do the right thing to show benefits. You need to be very fair to show the benefits. And also, if you want hardware support, you need to run on simulators, which are going to run extremely slow. You don't have the luxury of running, let's say, billions and billions of instructions. So you need to be extremely careful. As a result, by nature, only, let's say, tens of researchers work on it, maybe hundreds maybe 100 if you push it really hard, right? So you won't see a whole lot of work building on it. But I think given that perspective, there's still a lot of work that built on it.
Okay, yeah, thanks.
Okay, sure. And I think the paper that I mentioned, I will try to find it in the break. The paper that I mentioned that did things in the runtime system, for example, is one work that was inspired by these ideas, and they tried to do it. Okay, let's do it on a real system without having the hardware support. What kind of performance benefit will we get? And they did show significant performance benefits actually on a real system. Okay. Okay. Maybe I will cover the next work and then we will switch gears, take a break and switch gears to data marshalling. So basically, can we make better acceleration decisions is always the next question, right? And then in the next work, we tackled that. I'm not going to cover this in detail because if we do, then we will stay here until breakfast tomorrow, perhaps. Probably you don't want to do that. So I will just give you the key ideas of this. And here, now we're going to generalize the idea. We're going to generalize it to multi-threaded applications and multi-programmed workloads also. Basically, we take a step in this. Let's take a step back and let's look at the bottlenecks. So if you look at barriers, this is one form of bottleneck. It looks like this, right? So code reaching the barrier is on the critical path potentially, right? So if basically, this is not barriers basically. This is really critical sections. I was confused by the barrier over here, but critical sections, as long as you accelerate critical sections, you can accelerate this program, even though you may have barriers over here. This is something that was tackled by accelerated critical sections. BIS, bottleneck identification and scheduling, tackled other things like bottlenecks that are not critical sections as well, right? And we've discussed this. Okay, so basically multiple types of bottlenecks can be handled by bottleneck identification and scheduling. And if they change dynamically, they can be handled by bottleneck identification and scheduling. So lagging threads are a special example of bottlenecks. These are bottlenecks. As I discussed, BIS has a special mechanism like preemptive acceleration. So you need to somehow identify which thread is lagging, how much progress it has made toward the barrier, and then you need to somehow accelerate it. So basically, for example, if threads have equal amount of work, assume that for now. If you don't have equal amount of work, you need to normalize for that somehow. But assume that if they have made some progress toward the barrier, this thread has made 30% progress, this thread has made 40% progress. The thread that has made 30% progress is potentially a future bottleneck. It's lagging basically. So it makes sense to accelerate it at this point. And then keep track of these progress fractions and decide which one to accelerate. Of course, it's not easy to do. And you should really read the BIS paper and this paper to see how this is done. You need basically information from the software as well as information from the hardware to monitor this lagging threads in a barrier-based program. Okay, but now we have two problems at hand. Do we accelerate bottlenecks that are not lagging threads or lagging threads? Because these are a bit different from bottlenecks, because lagging threads, you need to preemptively accelerate them in a sense. Whereas here,
In the bottlenecks, you have a lot of information. Well, I'm not going to go back, but in the bottlenecks, you have a lot of information as to which ones became a bottleneck. And if you have multiple applications, which application do you accelerate? So let's take a look at the multiple applications case. You have two different applications. Application 1 has some sort of bottlenecks. Application 2 has some lagging threads, let's say. And then the question becomes, which one do you accelerate? Do you accelerate this lagging thread, or do you accelerate this critical section over here? If two applications have two different lagging threads, which one do you accelerate? So this becomes interesting, right? And acceleration decisions now need to consider both the criticality of the load code segments and how much speed up an application would get if you accelerate that. So you need to have a global view of the application as well, in a sense, for both bottlenecks and lagging threads, and for any running application. So this paper, similar to another paper that we discussed, like UHMEM, the hybrid memory management, utility-based hybrid memory management, this paper builds a utility-based management model to identify what would benefit from acceleration and who should basically be accelerated. So the goal is to identify performance-limiting bottlenecks or running lagging threads from any running application, to accelerate them on large cores of an ACMP. And the key insight is a new metric, basically. There's a utility of acceleration metric that combines speed up and criticality of each code segment. I'm not going to go through how we exactly compute it, because it takes some time to compute it. But you can imagine how you can express it. So utility of accelerating code segment C of length T on any application of length large T can be expressed as utility of code segment T, which is delta T over T. Okay, it's going to be a bit confusing, but let's break it into components. So there's a local speed up of the segment. If you accelerate the segment, how much local speed up you get? What is the fraction of execution time spent on the segment as part of the entire application? How important is this segment? And what is the global criticality of the segment in terms of global effect on the application? How much benefit would this application get? And on top of this, you can add how much benefit would the system get if you accelerate this application compared to some other application. So basically, this paper proposed a model to independently predict each of these three components. And on top of this, you can add the acceleration benefit of a particular application compared to other applications. And using this model, you can decide who should get the large core. Or if you have multiple large cores, how you should prioritize which bottleneck should get the priority. Okay, and that's the idea of utility-based acceleration. Basically, we have this model, we identify lagging threads, we have a set of highest utility lagging threads, we identify bottlenecks, we have a set of highest utility bottlenecks, and we control the large core using an acceleration coordination mechanism that's again described in the paper. And again, I'm giving you the high level of the ideas because the specifics are actually quite specific. You can imagine using this utility function and the model in different ways to actually achieve different goals. In this case, our goal was highest performance overall in the system. So the highest, the large core gets granted to the highest utility function, either bottleneck or lagging thread at any given point in time. But if you have multiple large cores, your large core control can consider multiple different types of applications as well. Okay. Okay, and these are the results. Basically, results actually are across 60 small cores, one large core, and 2 application workloads. And you can see that there's 55 workloads considered. And the comparison points are a multi-application aware BIS. So you can make BIS multi-application aware with very simple techniques. So that becomes still good, basically. There are some other proposals for multiple application scheduling in workloads, and they actually perform reasonably well depending on the type of the bottleneck in the applications. And UBA, utility-based acceleration, performs reasonably well as well. For not for all workloads, for some workloads, some other mechanisms are better, but on average, you can see that the curve, the UBA performance improvement curve, is better than many other mechanisms. Okay, and you can see the average results as well. And if you're interested, I've glossed over a lot of the details because we don't have time to cover, but a lot of the ideas in this paper are actually quite state-of-the-art and novel, if you will. And I don't know of any work that has improved on the ideas of this paper. Maybe there is, but I haven't really caught up with all the literature on this topic because there's a lot of literature also on topic. But I believe the ideas in this work are the state of the art in terms of how do you compute utility of acceleration, utility and the criticality of a particular segment, code segment, and how do you use it for acceleration decisions. Okay. And then, of course, the question is always, can we do better? And
at this point, I will take questions. And if there are no questions, then we're going to take a, let's say, 10-minute break. Okay, I think before I move on, I found the paper that I was mentioning that did this accelerated critical sections on existing multi-cores. It's called Remote Core Locking, Migrating Critical Section Execution to Improve the Performance of Multi-Threaded Applications. It was published at Usenix ATC Advanced Technical Conference in 2012. So if people are interested, they can take a look at it. I put the link on chat as well, so hopefully TAs will put it online. But I'd recommend people to look at it as well, since it's very similar to the ideas that we have discussed, except it's doing it on a real system and showing benefits. But the benefits are, as expected, are not as large as what you would see with hardware support. This also makes me think that there are not enough people working in this area for sure. Yeah, earlier we were discussing this. Now I maybe take it back. Maybe it's hard to even name more than 10 researchers working on fundamental and important topics like this, but they're so critical. Okay. Okay, now let's move on to another aspect that we have discussed, but we didn't go into detail about, which is this private data locality and how to handle it. Okay, so I'm going to give you another perspective of what we have talked about and what parallelization is about. And I think it's going to be a different perspective because this is really important, I think, for fine-grained parallelization. And I'm going to think about parallelization as staged execution. And the goal in this is to speed up a program by dividing it up into pieces. And the idea is very simple. You split a program code into segments, run each segment on the core best suited to run it. Now we're actually thinking about parallelization and heterogeneity at the same time, right? You're dividing up a program into segments in such a way that the segments are constructed or divided up such that you have in mind some cores that are best suited to run these segments, separate segments. I think this idea now combines what we think of parallelism and heterogeneity in these two lectures so far. And each core can be assigned a work queue, storing the segments that are supposed to be executed on that core to be run. And again, I'm using the term core here, right? Core is very general. You can think of this as a computation unit. It could be different types of cores, large core, small core. It could be, again, potentially FPGA. Potentially, it could be, the segment could be a data flow graph, and that data flow graph could be executed on every configurable engine, which is called the core in this particular case. It could be the GPU. It could be some sort of accelerator. So it depends on the size of the segment and where it's programmed to be run on, essentially, right? So of course, if it's general purpose, then these become cores, but you can always specialize each of the cores to suit the segments. That's why I think this idea is quite powerful, and there needs to be more investigation of the stage execution model and how to adapt it to more scalable systems. So of course, the benefits of this high-level idea is you can exploit segments or critical paths using specialized and heterogeneous cores. You can exploit inter-segment parallelism. That's where parallelization comes from. And it can improve the locality of within-segment data, as we discussed, right? By ensuring that a segment executes and the segments that operate on the same data execute on the same core, you improve the locality of within segment data, as we have seen with accelerated critical sections, right? Things that touch the same lock and same shared data execute on the same core. That's the same idea. But you can generalize this for any type of data. The data doesn't need to be just lock and shared data. It could be any type of data, right? It could be the data in the stage of a pipeline parallel program, because pipeline parallel program can be divided into stages based on which segments actually operate or which stages operate on which data. And if you execute the same instances of the same stage in the same core, then you actually get locality benefits. Okay, as we have discussed. So there are many examples of the stage execution model: accelerated critical sections, bottleneck identification and scheduling, of course, producer-consumer pipeline parallelism, as we have discussed. And there are many different task-level parallelism models that have been proposed in academia as well as implemented by industry. In the early times, Intel threading building blocks, for example. Apple had this Grand Central Dispatch.
And special purpose cores and functional units are also examples of this. So basically, if you think about it conceptually again, and it's always good to think about things conceptually first, stage execution model looks like this. You have some program with loads and stores and other instructions. You split the codes into segments. There's a reason why I specifically focus on loads and stores, because we're going to talk about inter-segment data. But it's about basically specifically, you split the code into segments of different computation, as you can see. And you have these 3 segments. And then you execute the different segments on different cores. Instance of S0 go to core 0. Instance of S1 go to core 1. Instance of S2 go to core 2. And each of those cores can be specialized for the segments that they execute. Okay, now let's take a look at segment spawning. So basically, this may be how things behave. Core 0 is executing segment 0. It spawns segment 1. And that in turn spawns segment 2. This is one way of spawning segments. It doesn't have to be regular, of course, like this. But this is one way of creating segments and launching segments in the other cores. And also communicating with the segments, potentially. Even though spawning doesn't mean that you spawn necessarily, you may be calling the segment, but the segment may already be present executing in that core to begin with as well. Okay, so let's take a look at these 2 examples. I'm going to basically map accelerated critical sections and pipeline parallelism to this model of state execution. And it's very easy to map these. So accelerated critical section, the idea, remember, was to ship critical sections to a large core and as asymmetric multi-core. Segment 0 is a non-critical section. Segment 1 is the critical section. That's it. And the benefit is you get faster execution of critical section, reduced serialization, and improved lock and share data locality, as we discussed. Let's take a look at and map producer-consumer pipeline parallelism. That's also very easy to map. Idea, remember, is to split a loop iteration into multiple pipeline stages where one stage consumes data produced by the previous stage, and each stage runs on a different core. In this case, segment n is equal to stage n, basically. That's it. And you get stage level parallelism and better locality in each stage, because hopefully you split your loop iterations into multiple pipeline stages based on which stage operates on which data, based on data locality, basically. And hopefully you get faster execution, as we have seen in prior works. Okay, so one problem with these stage execution models in general, not just accelerated critical sections, is the locality of inter-segment data. So core 0 is executing segment 0, core 1, segment 1, core 2, segment 2. When core 1 touches a location, in this case, location Y, that was generated by a prior core, by some other core, it gets a cache miss because some other core generated this data. You can see that core 0 generated that data. So you need to transfer the data from core 0's cache to core 1's cache, or main memory in the end, right? Depending on where their data resides. But probably from the cache of core 0 to core 1. Okay. Similarly, this load Z that's executing on core 2 gets a cache miss because the Z was generated by segment 1, right? And you need to transfer Z. Okay. So we've seen this problem in accelerated critical sections, right? Critical section incurs a cache miss when it touches data produced in the non-critical section, thread private data. And that thread private data needs to be shipped to the large core. And that's what the cache miss is about, basically. Producer-consumer pipeline parallelism. A stage incurs a cache miss when it touches data produced by the previous stage. And that data needs to be communicated through a cache miss through the cache coherence protocol again. And performance of stage execution is limited by these inter-segment cache misses. And we look at what if we eliminate all inter-segment misses, and take this with a grain of salt, because I don't think the study actually shows the full potential of mechanisms. But you can see that on some workloads, if you actually get rid of all inter-segment misses, you get about 10% performance. If you get rid of all inter-segment cache misses in pipeline parallel workloads, you get 20% performance. And I'm going to show you a mechanism that gets almost all of the performance improvements of eliminating inter-segment cache misses. And actually, this problem scales worse into the future as you increase the number of cores, as we will discuss. So the numbers may not be that dramatic over here. And also, this is general purpose. It's average across many applications, right? It's not specialized to any application. It's average across many applications. As a result, numbers tend to be overall lower in general, right? It's easy to accelerate one application by 10x. It's much harder to accelerate 10 applications by 10x with a single mechanism, I should say. That's why it's good to keep these numbers in context always. Okay, So let me define some terminology first. You've seen this picture before. Basically, I'm going to define intersegment data as a cache block that's written by one segment and consumed by the next segment. Basically, this is data produced by one segment and consumed by the next segment. You can also think of this as producer-consumer data, if you will. And you can see that the cache block Y and cache block Z are examples of this over here. And generator instruction is the last instruction that writes to an intersegment cache block in a segment. So let's take a look at this. In this case, in segment 0, the store to Y is to an intersegment data. As a result, it's the generator instruction because it's the last instruction that writes to the intersegment cache block. In this case, store Z is the last instruction that writes to the cache block that houses intersegment data Z. Okay. And the key observation and idea in this work is, again, very simple. Once you see this, the observation is that set of generator instructions is stable over execution time and across input sets. And the idea is to have the compiler identify the generator instructions. This could also be done in hardware, by the way, but we're going to discuss the compiler approach. Hardware can also do it. And then record the cache blocks produced by generator instructions, and then proactively send such cache blocks to the next segment's core or cache before initiating the next segment. So that hopefully, whenever the next segment needs that intersegment data that's produced by the generator instruction, the data is already there in its cache. So it's a form of push mechanism. You're pushing data to some other core that you think is going to need it, so, before that core needs it. So it's kind of the opposite of prefetching. As opposed to the core prefetching the data, the core that's generating the data is pushing the data to the core that needs the data. Okay, and that's discussed in this work. Okay, so let's take a look at how this works basically in a bit more detail. So the compiler or the profiler identify these generator instructions and inserts these data marshal or push instructions. And eventually you have a binary containing generator prefixes and marshal instructions, as we will see. And hardware records these generator produced addresses and marshals the recorded blocks to the next core when the time comes. Okay, so all of this could be done in hardware actually. We do some things in compiler to reduce cost. But again, you can think of moving everything into hardware in this particular case because generator instructions are relatively constant and you can identify them. They're not hard to identify using the cache coherence protocol. And everything can be done in hardware seamlessly in this particular case. Okay, now let's take a look at the compiler profiler support, which could be potentially migrated to hardware as we discussed, right? So this is the profile. Basically, we have a profiling algorithm that profiles the program and figures out which data is intersegment data. Basically, that is touched by one segment that was produced by a previous segment or some other segment. It's called intersegment data. And we've identified the generator instructors. Remember, the generator instructor is the last instructor that's producing the data. There could be multiple generator instructors. Why? Because there could be an if-else clause, for example. And depending on if clause, you have one instruction generating Y. Depending on the else clause, you have another instruction generating Y. So there's no such thing as there's no such rule as there has to be only one generator instructor. There could be multiple generator instructors. Okay, so basically the compiler marks the last instruction as the generator instruction. If there are multiple last instructions in the profiling round, you mark multiple instructions. And then the compiler inserts those marshal instructions. So we mark the generator instructions, as you can see in this particular case. And then we insert marshal instructions. So marshal instructions denote when to send the intersegment data, when to push the intersegment data to the next segment, and then where to send it, which is essentially what is the next segment, which next segment will need the data. And these can be inserted using using marshal instructions essentially. Okay. Okay. So hopefully that's easy. Basically, by profiling, you could do this. And again, this profiling can be done by compiler or hardware. I'm not going to go into the details of it. In fact, in some cases, doing it in hardware is easier because in hardware, you can do the logical to physical core mapping easier. If you do it in compiler, you need to map where to send, like which core to send. Basically, you need to bind the virtual core to the physical core that's actually executing the segment. So it's not that easy. Well, it's not that. Basically, there needs to be a mechanism to do that binding of the virtual core to the physical core, because the compiler doesn't know which physical core the segment will be executing on, right? So if you do this profiling in hardware and insert the instructions in hardware, then it's a lot easier because you get rid of that virtual to physical binding problem. Okay. Any questions? Okay, there's some comments saying that my mic cable is scratching on something. Are people hearing me well? So, is it better now? I don't know. I don't have my nice mic right now, so. Okay, let's try again. Let me move the cable over here. Is it better now? No? Okay. Okay, how about on Zoom? Anybody hearing me? Okay.
Yeah, I can hear you on Zoom. I don't know.
Okay, is
what
it
about
fine?
the room? Yeah, on Zoom it's fine. I don't know about the room though.
Okay, I hear on Zoom it's fine. So I'm assuming that it's fine unless someone complains in the room right now. Okay. So how do we actually make it work, basically? Let's discuss this. I want to remove this video panel, basically, or floating meeting controls. Okay, it's gone now. So basically, this is the support we need. We need a profiler and compiler that marks the generators and inserts these Marshall instructions. As I said, this could be done in hardware also. We need to have the ISA modified so that you can have the generator prefix and the Marshall instructions. And again, this can be done in hardware. So you get rid of the profiler, compiler, and ISA support if you actually do everything in hardware. And we need the library and the hardware to bind the next segment ID to a physical core, as I discussed. So you can do all of that in hardware as well. So that only increases the hardware cost, basically. But maybe it's fine to do it in hardware as well. Our later results show that doing it in hardware is not that bad. If in hardware you need a Marshall buffer, which stores physical addresses of cache blocks to be marshaled. I will show you an example of this. And we find out that it can be very small, a small number of bytes per core. You need to have the ability to execute generator prefixes and Marshall instructions. You need to have the ability to push data to another cache. So as I said, this is exactly opposite of prefetching, if you will. Prefetching prefetches data from the core to the core's cache. Marshalling or pushing data pushes the data from some other core to another core's cache, right? So you need to make sure that that support exists. That support exists actually in existing coherence protocols. If you actually update the data in some cache using data from some other core's cache, then you actually are updating, pushing data using a protocol, update-based coherence protocol, as we will discuss. Before I give you more examples and results, let's talk about the advantage and disadvantage of this. This gives you a timely data transfer. You push data to the core before data is needed. You can marshal any arbitrary sequence of lines because you're just identifying generator instructions. You're not identifying patterns like prefetching. Prefetching actually doesn't work in this case because you need only a few number of cache blocks to be sent to the core. And if you want to wait for the prefetcher to warm up, it takes a long time to warm up actually for the prefetcher to recognize the access patterns. So prefetching doesn't work, but this also doesn't suffer from the downsides of pattern-based prefetching because if the identifier instruction generates an address in some arbitrary way, that's fine. You still get the data and push the data to the large core. Well, large core in this is accelerated critical sections case. And then we have low hardware cost because we don't do everything in hardware. Profiler marks the generators. There's no need for the hardware to find them. This leads to a little bit more hardware cost if you want to do everything in hardware clearly. So disadvantages, this requires some profiler and ISA support. It's not always accurate because the generator set is conservative when you do the profiling. If you actually have a lot of generators, for example, this leads to pollution at the remote core and wasted bandwidth on the interconnect. But it's not a large problem as the number of inter-segment blocks are usually small, as we will see. Okay, so let's take a look at how this operates pictorially. So we have accelerated critical sections. We have the small core and the large core. And you can see that small core executes these load store instructions. And we have a generator instruction here. And we have a critical section call, which implicitly serves as a Marshall instruction. So, okay, let's step through it. So we have a Marshall buffer in the small core, which is going to house the lines that are going to be marshaled to the large core's cache. And basically, small core keeps executing. When it gets to generator instruction, it generates the address, placed into the L2 cache. And then when it gets to the Marshall instruction, which is the critical section call, or you can put a separate Marshall instruction if you want to be more timely. Then the Marshall buffer accesses using the addresses that are accumulated over here, accesses the cache. gets the data associated with the cache, sends it to the L2 cache over here, and installs the line associated with that data, with that address Y, into the L2 cache of the large core. It could be also L1 cache. This is just a demonstration with the L2 cache, as you can see. Okay, hopefully that makes sense. And hopefully, when the critical section gets executed on the large core, you get a cache hit. And that way you hide the penalty of moving the data, private data, that's generated by the store Y from the small core to the large core. And this works for arbitrary number of cache blocks as long as you have space in the Marshall buffer, as you can see. Okay, so let's evaluate it for accelerated critical sections. Again, the methodology is similar to what we had done with accelerated critical sections. And the performance improvement you get is significant. Basically, we get almost all of the potential performance improvements of the ideal. And in cases where we don't get the potential, for example, here, it's because we don't have enough size in our Marshall buffer. So you can make the Marshall buffer a bit larger and you get the potential performance improvement. Basically, this is a mechanism that buys you almost all the potential performance improvement of eliminating inter-segment cache misses with accelerated critical sections. Okay, let's take a look at the case of pipeline parallelism. So pipeline parallelism works even with symmetric cores, right? You don't need asymmetric cores here. Core 0 executes stage 0, core 1 executes stage 1. Okay, and they both have Marshall buffers. When core 0 gets to a generator instruction, it inserts the address into the Marshall buffer. When it gets to a Marshall instruction, it basically takes the addresses one by one, accesses the cache, and sends the data to the L2 cache of the destination core, in which case, in this case, it's core 1. And then you keep doing this for every address that was generated. And hopefully, when core 1 executes load Y, it's a cache hit. So of course, you can improve the timeliness, etc., by ordering the Marshall instructions, putting the generator instruction early, etc. You can play all sorts of code optimization tricks to make this more timely as well. And the evaluation with pipeline parallelism applications shows that the performance improvement is, again, close to the ideal. And again, when you don't get the ideal performance improvement, it's because your Marshall buffer is smaller than it needs to be. Okay. Any questions so far? Okay, so let's quickly analyze the coverage, accuracy, and timeliness of this. So coverage means that what fraction of the inter-segment misses do you cover? And it's very close to 100% in accelerated critical sections. It's close to 90% in pipeline parallelism. And because the reason we don't cover 100% is because of the, let's say, we don't correctly identify generated instructions all the time, right? Because profiling is not perfectly accurate. So with better profiling methods, you can improve coverage. There's always a trade-off between accuracy and coverage. You can see that the accuracy is lower because we send more data than we need, because we identify more conservative instructions in general than actually are needed. For example, you have a generator instruction that sends data, and that data may not be needed because some other generator instructions are going to override that data. Why? You may have the second generator may be executed under an if clause, right? The first generator sends the data, and that data is needed if the second generator is not executed. Make sense? So in that case, we send more data than needed, but then as a result, accuracy is lower, as you can see. But accuracy is not that bad also. And medium accuracy does not impact performance because there are only a small number of cache blocks that are marshaled that are sent for the average segment, 5 to 7 blocks. Timeless is actually quite good, as you can see, even though we didn't do a lot of optimizations. More than 80% of the time, whenever the destination core needs the cache block that's coming from some other segment, it has it in its cache. So it's more than 80% of the time. So of course, you can improve this, but the improvements will lead to incremental benefits that is going to get us closer to the ideal performance improvement. Okay, the more important thing is scaling, I think. Scaling is important because as you scale the number of cores, the performance improvement increases. As you scale the interconnect latency, which is again the trend, the performance improvement increases. As private L2 caches become larger, the performance improvement also increases. Why? Because inter-segment data misses become a larger bottleneck. These are actually very interesting special misses, right? They're communication misses, right? You're communicating a piece of data from one core to another core, one thread to another thread. They're really communication misses. We're going to talk about
misses when we talk about coherence, cache coherence a lot more. But this is not a capacity miss. This is not a conflict miss. And this is not a cold miss also in caches. It's really a communication miss. If you actually communicated early enough, like we're trying to do, you would get better performance. And if you have more cores, you have more communication, because hopefully you will parallelize your program even more, and more communication leads to more larger bottleneck. If you have higher latency to communicate the data, you have longer stalls due to communication. And if you actually have something like data marshalling, you would actually overcome the latency better. And if you have a larger L2 cache, if you have larger caches, caches don't help these misses, because these are communication misses again. If the data is not communicated to you, you're not going to be able to cache it, regardless of however big your cache is, right? Because the data is updated by some other segment, and you have to wait for that update to happen. That's why these misses are actually quite special, and they need to be handled differently. And this is one important way of handling them differently. Okay, so there are other applications of data marshalling, basically, which I'm not going to discuss in detail. There are actually a lot of interesting applications of stage execution models. If you generalize like special purpose remote functional units, like full heterogeneity in the system, all of the cores can be fully heterogeneous. Different task parallelism models that are employed in industry, for example. There are other proposals in academia like computation spreading, thread motion, and migration. I'm not going to go into details, but these basically specialized computation. Some sort of computation is executed on a specific type of core. For example, computation spreading, I believe, says that if you have system level code, like operating system code, executed on a special core, because the system level code can benefit from that because of the data locality, etc. It's a form of stage execution, basically. Thread motion and migration also does something similar, basically, for code that's more critical and less critical. So basically, the idea can be applied to many other stage execution models that we didn't consider. And it can be an enabler for more aggressive, finer-grained parallelization in heterogeneous systems, because this sort of idea lowers the cost of data migration in general. And data migration in general has an important overhead in remote execution of code segments. And remote execution of finer-grained tasks can become more feasible, which can enable finer-grained parallelization in multi-core and heterogeneous systems in general. Okay, I said a lot over here, but I think we've covered a lot of this earlier, so I'm not going to go into details again. Okay, so I think I've summarized. I don't want to summarize everything again, but basically, this is an idea that can enable very fine-grained remote execution, because it eliminates the remote misses that can be caused due to the way you're orchestrating execution across multiple different cores. So I believe it can also enable new models. The jury is still out, of course. There needs to be more research done in this area. Finer-grained parallelization is important. I think it's easier to do coarser-grained parallelization, right? So the models that we have today with accelerators are more coarser-grained. What you do is you have a CPU, you have a GPU, you offload the code from the CPU to GPU, and I assume that the GPU will execute for hours. Okay, maybe minutes. Minutes is still very coarse-grained, right? What if you want to actually, what if you have a CPU and GPU that can communicate very fast with each other? They're on the same die, and you want to take advantage of the different characteristics of the CPU and GPU. Now that becomes a different programming model, and also different trade-offs in terms of communication and computation. And we need to address those trade-offs. People currently are addressing the coarse-grained paradigms. Well, I have a coarse-grained accelerator, I offload computation. But once coarse-grained opportunities are done, you're back to fine-grained parallelization. And how do you actually get benefits of these fine-grained parallelization and fine-grained systems that put together these different heterogeneous components and offload fine-grained execution, like tens of instructions, hundreds of instructions, maybe even less than tens of instructions? How do you actually take advantage of that? I think this sort of ideas becomes very powerful in that particular case. And I think there needs to be more research to be done, because this fine-grained execution is going to happen over time, especially when we keep integrating the CPUs and GPUs on the same die. That's as it's happening today, right? And I think we're going to do that more and more. Okay, and if you're interested in this, there's the title should be more on data marshalling over here, but there's a lot more in the paper and the follow-up paper on this one. Okay, let me quickly switch gears, and we're going to talk about other use of heterogeneity, but I will mention that current systems have heterogeneous cores. I mean, clearly ARM was one of the earliest ones to have it with little and big. And clearly Apple system has it. I think the current Intel system has even more cores. They have, this is a picture of Alder Lake, and they have 8 powerful cores and 8 efficient cores, as you can see. And again, there's no reason why these ideas cannot be applied to these cores over here. But let me switch gears a little bit and talk about other use of asymmetry. And I think these are also interesting. Some of them are going to be overlapping, but some of them are not going to be overlapping, especially the first one. And this first one is the use of asymmetry for energy efficiency. And you can see that this was one of the first proposals for heterogeneous multi-core. Why don't we implement multiple types of cores on a chip, monitor the characteristics of the running thread, meaning sample energy and performance that we get on each core periodically, and dynamically pick the core that provides the best energy and performance trade-off for a given phase. And the best core depends on the optimization metric in this case. So basically, the idea over here is you don't have a multi-thread application. That's a different problem, basically. You have either a single thread application or multiple threads from different programs. You dynamically pick the core that provides the best energy performance trade-off for each thread, depending on the phase the thread is executing at. And that's the idea. And these folks were quite clever, actually. What they did was they basically said, this is one way of actually constructing a symmetric multi-core. If a company has produced different types of cores over generations, this is the Alpha company, Digital Equipment Corporation. EV4 was, I think, Alpha 21064. EV5 is 21164. EV6 is 21264, which is a famous 21264 processor. And this is 21464, I think, EV8. And you can see that their relative sizes are quite different. They say relative size of the alpha core scale to 0.1 micron. EV8 is 80 times bigger, but provides only 2 to 3 times more single-threaded performance. This is kind of similar to what the Intel paper that I mentioned earlier said, actually. Basically, you have a huge core, and the performance is different. But clearly, you have a lot more performance over here. And basically, they study power and relative performance of the alpha core scaled to that nanometers, and performance is expressed normalized to EV4 performance. And you can see that there's a performance curve and there's a power curve. So you pay a lot for the performance you get in terms of power. So the power of EV8 is a lot more. So you can actually do the calculation, right? The power increases by, okay, let's say 5 to, let's say 100. Power increased by 20x to get 2x performance. That's similar to what Intel actually said in that ICCD 2004 paper that I mentioned yesterday. Best of both throughput and latency. So these folks basically said that, why don't we actually have all these different types of cores on the same chip and monitor execution? So they're coming from a very different angle, as you can see. We've already designed these cores. Why don't we put them on the same chip and exploit the best characteristics of each core? How do we put them on the same chip? It's easy, basically. Glue them together and put some interconnect, etc. They don't discuss those issues that much in this paper. But you can monitor the performance you're getting. This is the performance of an application for when it executes on EV4, for example, when executed on EV5, EV6, EV8. So clearly, EV8 is highest performance, especially on some phases. But in some phases, they're very similar, as you can see. And then you can basically create a switching mechanism. It could be done at the operating system level. It could be done at the runtime system level. It could be done at the application level, potentially, right? And basically, you switch such that you pick the best core that's the best for energy. And you can see that in most cases, it's EV6. In some cases, it's EV8. In rare cases, it's EV4. So this is the runtime mechanism that runs and picks the best core so that they can migrate the application, full application. Here, they're migrating the full application from one core to another. There's no one thread or another thread. The full application gets migrated because the full application is single thread. And then if you actually do the core switching for energy delay product, now you actually, it becomes more interesting to use EV6 and EV4. So energy is actually biased to finishing the program quickly, which is average power over here. Energy delay product is actually looking at both of them at the same time. But you can read the paper for more detail. They have the more analysis of the results. So clearly, this is an interesting idea, and this is a good idea also. And this is an easier use of heterogeneity. So the advantages are there's more flexibility in energy performance trade-off, and you can execute computation
on the core that is best suited for it in terms of energy. So from an energy performance perspective, this idea makes a lot of sense. Clearly, it has some disadvantages and issues similar to what we had in accelerated critical sections and other ideas. Like if you have incorrect predictions and sampling, you decide on the wrong core. As a result, you get reduced performance and increased energy. And this is a bit harder to overcome because you're moving the full application from one core to another core. So in a sense, whenever you move an application from one core to another core, you need to warm up the caches in that core, unless you have shared caches, for example. There's overhead of core switching, including the caches. The same advantage of this disadvantage of asymmetric CMP, designing multiple cores, exists. It's not clear if it's the best idea to actually design the cores, use the cores that you've already designed. It's clearly a low-cost idea, but it's not necessarily the best fit core for different phases, right? So maybe designing asymmetric cores to fit the phases is probably a more principled approach, but it's a higher cost approach. You need to have phase monitoring and matching algorithms. There's a lot of proposals in literature on phase monitoring and matching. That's interesting. What characteristics should be monitored? Once characteristics are known, how do you pick the core? They basically deal with these problems. And you can imagine those, right? If you see, for example, a similar instruction mix, for example, you can say, oh, I'm in the same phase as before. If you're executing the same instructions, for example, if you look at the program counters and summarize them using a hash function, if in a later phase you see that you're executing similar program counters because your the hashed values are very similar of the program counters, you can say, I'm going to execute that same phase. So let me use the same core that I believe was good last time for this phase. And of course, you need to explore also, how do you sample? How do you figure out which core is the best for which phase? This paper proposes a sampling algorithm that may be heavyweight. So there are some issues over here that are harder to tackle than what we have discussed earlier. Earlier, we wanted to only put the bottlenecks to the large core, right? Here, anything can go to the large core, and you need to decide what goes to the large core based on a performance energy trade-off. Sometimes you may need to sample to be able to make that performance energy trade-off. Later, people have built models. Can we model what kind of performance and energy benefits we would get if we were executing on core X while we are executing on core Y? Clearly, this is a harder problem. You don't need to execute on core X to predict what your performance and energy would be on core X. You can be executing on core Y while you're doing that. And then based on that prediction, you decide whether or not you switch the cores, right? And there's a lot of literature on that topic, actually, modeling the performance that you would get and energy you would get on some other core while you're executing on another core. Okay, so clearly this led to a lot of research, and there's a lot of interesting research ideas here, which I'm not going to get into. Any questions? Okay, so I think we already covered the advantages of asymmetric and symmetric, but maybe from an energy perspective, it's good to think about advances also. We haven't talked about energy as much, but I would like to cover energy in this remaining portion of this lecture. But basically, asymmetric cores can provide better performance when thread parallelism is limited, and they can be more energy efficient by scheduling computation to the core type that can best execute it, as we have seen in this work. But disadvantage is that, I mean, always asymmetry requires designing more than one type of core. But is that true always? As these folks show, you've already designed more than one type of core. Why not use the older cores, right? And we will see some other examples of this. You can actually have some natural asymmetry as well, because fundamentally, because of process variation, some parts of the chip you can clock much higher, some part of the chips you can clock much lower. As a result, fundamentally, you have some asymmetry in frequency also. Scheduling becomes always more complicated whenever you have asymmetry. What computation should be scheduled on the large core? Who should decide, hardware or software, runtime system or the application? There are many questions over here. Managing locality and load balancing can become difficult if threads move between the cores, especially transparently to the software. So there's locality issues and there's load balancing issues that you need to deal with. And cores have different demands from shared resources. So maybe you should have asymmetry in the shared resources as well, as we have discussed in quality of service mechanisms, right? So we discussed quality of service mechanisms mainly from a symmetric perspective, but when your cores become asymmetric, you need to adapt the quality of service mechanism to that asymmetry as well. Okay, so let me talk about how to achieve asymmetry in there are two different ways of achieving asymmetry also. Basically, you have static, type and power of cores can be fixed at design time. And there are two approaches to designing faster cores also. One is high frequency, enabling high frequency cores. Some cores are fundamentally high frequency, or some cores are fundamentally more complex and powerful with entirely different microarchitecture, or a combination of both, of course, right? So these are static asymmetry, I call it. Basically, you don't change asymmetry dynamically. And static asymmetry may be natural because of chip-wide variations in frequency, as I mentioned, because some parts of the chip you cannot operate as high as some other parts because of process variation. Okay, that's interesting, clearly, but dynamic asymmetry may be more powerful. In this case, type and power of cores may change dynamically, right? And again, I'm calling cores, but you can think of these as computation units, constructs. It could be FPGAs, it could be GPUs, etc. And there are two approaches to dynamically create faster cores. One way is boosting frequency dynamically. So if you have a limited power budget, you can boost the frequency, right? So that you don't exceed the power budget, and you can reduce the frequency of some other cores. That way you can actually create some asymmetry in the cores that are executing. Or you can combine small cores to enable a more complex and powerful core. This is from the general purpose perspective, right? But of course, there's also reconfigurability, right? You can actually create some reconfigurable device, or portion of your device can be reconfigurable, and you can reconfigure your device to execute a data flow graph dynamically, such that that data flow graph executes very fast, right? And I think that's a form of dynamic asymmetry as well, as long as you can do the reconfiguration relatively quickly. Okay, so let's take a look at this boosting frequency dynamically a little bit and combining small cores. I think combining small cores to enable a more powerful complex core, that has been studied actually. There are multiple works in that area. Core Fusion, Morph Core are example works, and they both try to build a more powerful core. And whenever needed, you can scale it to small cores. And whenever you can expand it to a large core. It's not an easy task. And having some multi-threading capability and reducing that multi-threading capability helps, of course. And maybe there are some other approaches to this also. I think clearly reconfigurability is one approach, but maybe there are some approaches to building general purpose cores as well. Let me talk about asymmetry via frequency boosting, because I think this is an interesting approach. Clearly, it's an easier approach, as we discussed, and it's an approach that is implemented almost immediately by industry, because it's very easy to change the frequency of a processor. And people already do that. Why not do it in an asymmetric symmetric multi-core processor and create asymmetry, such that you can execute important parts of a program this way? This is the idea of asymmetry of frequency boosting. You can do this statically, meaning assign some cores to be statically higher frequency, some other cores statically lower frequency. So it's not dynamic. Or dynamically, you can basically change the frequency of cores dynamically. Static means that due to process variations, cores might have different frequencies. This is interesting, but it has limited usage space. Basically, you simply hardwire or design cores to have different frequencies in this case. Dynamic means that it's actually proposed by this paper, which I'm going to briefly talk about. You take advantage of dynamic voltage and frequency scaling, and you basically accelerate serial bottlenecks this way. The idea in this paper is very simple. It's very similar to accelerated critical sections. Well, it's not similar to accelerated critical sections, sorry. It's basically very similar to accelerating serial bottlenecks, meaning MDAL serial part, by shipping that serial part to a large core. Here, instead of shipping it to a large core, what they do is they boost the frequency of the large core. Clearly, these are two different approaches to accelerate a serial bottleneck, right? They use dynamic voltage and frequency scaling in this case. Okay, and I'm borrowing from the paper right now. The goal is to minimize execution time of parallel programs while keeping power within a fixed budget. And they basically realize that there's an MDALS bottleneck serial part, and then there are parallel parts. Clearly, they don't deal with the bottlenecks in the parallel parts like we have been dealing with. But basically, they say for best serial and parallel performance, they vary the energy expended per instruction based on available parallels. So basically, they take an energy viewpoint. So if you look at power of a processor, it's energy per instruction times instructions per second. If you do the calculation, you will get power in the end. And power, you have a fixed power budget. But you can manipulate energy per instruction and also instructions per second such that you don't exceed a fixed power budget. That's the idea. Remember, in the earlier papers we discussed, some cores have higher energy per instruction, but they also have higher instructions per second, right? as long as you don't exceed your fixed power budget, you can decide which core to execute on. You can do a similar trick by just adjusting the frequencies. Basically, for a fixed power budget, you run the sequential phases on a high EPI processor, meaning a processor that has high energy per instruction, that has high, essentially high frequency in this particular case. And you can run the parallel phases on multiple low EPI processors, basically processors that run at low frequency. And this way, your power budget remains constant. That's the idea. Okay, so they're going to use DVFS, dynamic voltage and frequency scaling. In phase of low thread parallelism, run a few cores at high supply voltage and high frequency. In phase of high thread level parallelism, run many cores at low supply voltage and low frequency. So it's very similar to the idea of asymmetric cores, except asymmetry is achieved by frequency boosting as opposed to shipping to a large core, right? And I'm going to mention the other paper that I mentioned very early on when we talk about asymmetry. This is the Intel paper. Actually, the other one's an Intel paper also. The one that we're talking about is an Intel paper also, but this one's an Intel paper. Here, basically, they talk about how you can change the energy per instruction and how much time it takes to energy per instruction and what is the action you need to do. So voltage to frequency scaling basically gives you an energy per instruction range of 1 to 4, let's say, between the highest voltage setting to the lowest voltage setting. And it takes time, 100 microseconds in this case, to ramp up the VCC, basically, voltage. And basically, the action is to lower or increase the voltage and frequency clearly. So it's reasonably fast, as you can see, right? But it's not as fast as some other options over here, as you can see. So asymmetric cores give you a larger range, according to this paper. I believe that it's even larger, actually. And time to alter, time to move the data is actually shorter, as you can see. It's shorter than the voltage ramp up. Basically, you're migrating threads from large cores to small cores. Variable size core, basically here you design a core and you basically change them, you make it configurable. Basically, you change the configurability such that it becomes high power or low power. It's faster to do that. You reduce the capacity of the processor resources, as they say over here. And these are their numbers, basically. They're expected numbers. Take this with a grain of salt. They're not necessarily correct, I would say. Speculation control, basically reduce the amount of speculation you do. Basically reduce the number of branches you predict alive in the machine, for example. That gives you less EPI range, but the time to alter the EPI is very quick. Basically, you can quickly modulate this action, basically, to change the EPI. So you can imagine other things over here, right? Perhaps we configure an FPGA, for example, ship the data to a GPU, etc. So there are other methods, actually, and there are other methods with different EPIs. One thing that's missing in this picture is IPS. They don't basically talk about instructions per second over here. You should add that over here. And there are different time to alter EPIs, and there are different throttling actions, if you will. And clearly, boosting frequency of a small core versus large core is already implemented. Intel Nehalem, IBM Power 7 were some of the first processors to implement it. The advantage is it's very simple to implement, no need to design a new core. Parallel throughput does not degrade when TLP, thread level parallelism, is high, whereas large core kind of degrades it, as we discussed, and preserves the locality of the boosted thread. But compared to accelerated critical sections, or something like that, basically large core, it doesn't improve the performance if the thread is memory bound. So frequency, increasing the frequency of the core improves the computation speed, but it doesn't help you with the memory speed, right? A large core with better prefetchers, larger caches, larger microarchitecture to tolerate misses helps memory bound threads as well. It doesn't reduce the cycles per instruction. The performance equation, remember, it's increasing frequency. Frequency is one component, cycles per instruction another component. Basically, it doesn't help with the microarchitecture. So that's why asymmetric multi-core can potentially still has benefits over boosting frequency. And changing frequency and voltage can take longer than switching to a large core, as the Intel paper also mentions in the previous work. Okay, and that brings me to the last slide, basically. I think we're just on time. If there are any questions, I'd be happy to take them. Okay, there's one question. Please go ahead.
Yeah, it was about something that was on the previous slide on the one of the disadvantages. It says it doesn't improve the performance if a thread is memory bound, but
yes,
if a thread is essentially waiting on memory, can't we just sort of save power by just like cutting its power, boosting the other threads instead? So wouldn't that sort of overall improve the performance?
Yeah, potentially, but I think yeah, I think that makes sense. I mean, what you said certainly makes sense, right? If a thread is waiting for memory, like reduces frequency in the core because it's going to wait for a long time anyway. And people have proposed that actually. There are papers that are written to propose that if you have a long latency cache miss, switch to a lower voltage and frequency operating mode, and you can boost the frequency of other threads potentially, right? Yes. Yes, but I think here I'm comparing from the perspective of if you want to improve a thread's performance, do you improve that particular thread's performance by boosting frequency? And clearly, if the thread is memory bound, no, right?
Yeah. Okay.
Okay, but that's a very good point. You can improve the overall system's performance by adjusting the frequencies in different ways.
Would there be a way to sort of like instead of, yeah, if it's waiting on memory, somehow also like use that leftover energy to boost memory frequency? Would that
So
be?
Now you're getting into new ideas, and that's I like it actually. Yes, certainly, right? Basically, you have a limited power budget. You can use that power in the core or in the memory. Now, what you're suggesting is shifting the power to the memory side, right? And exactly that, those ideas have been also proposed. This is called power shifting. And people have proposed that when a thread is memory bound, shift the power to the memory side, increase the voltage and frequency, reduce the voltage and frequency of the cores. But that's an excellent idea. But that requires more work, of course.
Right, yeah, because then we would need access to, yeah, sort of have this whole system be outside of the core pretty much.
Exactly. And I mean, to be fair, those things already exist actually. People already do this system level power management. Not everybody does it in the best way, let's say, but people try to do the system level power management by allocating the power between processor and the memory resources. The difficulty is usually ramping up the voltage. So it takes a long time to ramp up voltage. So it's very difficult to do this at finer grains, as that Intel paper mentioned, right? If we go back to that Intel paper over here, yeah, voltage and frequency scaling takes some time, basically. It may be even easier to actually switch to another core, as long as you're not actually, you don't need to initialize a lot of state. So 32 kilobytes may be okay, for example, but if you're initializing 10 megabytes, okay, it may take too long. Okay.
Yeah.
Okay.
Thanks.
Yeah, thanks. Very good questions. Yeah, I think on YouTube, there's a comment also, these things don't scale that fast, especially on an individual request granularity. Absolutely true. You don't want to do this on an individual request granularity. But if you know of a phase where you're going to be completely memory bound for, let's say, microseconds and microseconds or milliseconds and milliseconds, then you can shift the power to the memory side, right, for that particular core. Okay, any other questions? Okay, then I think we're done. I have some backup slides. If you're interested, these backup slides are quite interesting because this is based on a position paper that we had written and position talk that we had delivered on a Computing Research Association workshop a long time ago, more than, I think, 12 years ago now, or something like 12 years ago, where I made a case for asymmetry everywhere. So you can have fun with those slides. Some of them are familiar, but some of them are interesting, like constructing the best fit chip for a given phase. I like this idea of whenever you're executing dynamically, you have these reconfigurable resources that are out there, configurable resources, and you basically construct a chip that's best fit for a given phase at any given point in time. For example, in phase 1, your chip may look like this, the green resources allocated to you, to that particular program. In phase 2, the chip may look like this, the red resources. In phase 3, the chip may look like this for that particular program. It depends on basically the characteristics of the program and characteristics of the different components that are kind of depicted conceptually over here. And I like this way of thinking conceptually about asymmetry in general. And I think this may be a long shot, clearly, but I think this is a very good way of thinking about asymmetry, enabling the best chip for each phase with these asymmetric resources all over the place. And you keep basically repeating this. And then you can morph software components to match asymmetric hardware components. So you can have different versions of software. I'm going because some people are listening. I'll finish soon. But you can basically have a version of software that's run for the first type of chip. And you can have another version of software that's run for the another type of chip. And you can merge them And you can have yet another version that's run for this third type of chip, right? And clearly there are many research and design questions, but I'm not going to go through this. And you can see some examples of this in the backup slides that I'm not going to cover right now. Okay, if there are no other burning questions, then I think we're done.